Hello there and welcome to Science for Sleep, where curiosity can stretch out on the couch and science takes its time wandering down the long hallway of questions. Tonight's quiet exploration will focus on something both terrifying and fascinating, something that sounds like the premise of an old science fiction novel, but is very much real. It is a place where the rules we know begin to bend and then simply stop working, a place where even light itself finds no escape. We're going to talk about the event horizon, often called the point of no return, the invisible threshold surrounding a black hole that separates the world we know from a realm we can only imagine. You've probably heard the phrase before, maybe in movies or in dramatic headlines, but here we're not rushing to explain it or wrapping it in mystery for the sake of it. We'll take our time, we'll look at it from the outside in, understand what it really is, and why scientists consider it such an important feature of the universe. Think of it as a shoreline, but instead of water and sand, there's the curvature of space and the pull of gravity, and stepping across it is like walking into an ocean with no bottom and no way back. There's nothing to hold on to, no rescue boat on the horizon, just a steady drift towards something you can't see. Before we start pulling at the threads of this idea, I'd like to know something. Where are you listening from right now and what's happening around you? Is it quiet where you are? Can you hear the hum of a fridge, the patter of rain, the occasional car passing in the distance? It's always interesting to think about how we can share the same moment. You there and me here, but still be in such different surroundings. That's not entirely unlike what happens with the event horizon, where different observers can experience the same situation in completely different ways. But we'll get to that. If you find these calm wanderings through science to be a good way to end your day, or even just a reason to slow down for a while, it would mean a lot if you left a like on this video and maybe subscribe to the channel. It's a small action on your end, but it helps this quiet little corner of the internet find others who might be looking for exactly this kind of pause. Now imagine you're standing in space, far from any planet, star or asteroid. All around you is darkness and silence. But ahead there's something different. At first glance it's not even visible, just a strange patch of sky, where the stars behind it seem to have vanished. You're looking at a black hole, or rather the space it occupies, because the black hole itself doesn't emit light. What you see instead is its effect on the space around it. As you approach, the familiar rules of physics, the ones that let us predict the path of a ball, or the orbit of a planet, still apply, but their predictions become stranger and stranger. Distances feel stretched, timescales seem uncertain, and you might notice the starlight bending in unusual ways as it passes close by. The event horizon is the boundary where all of those peculiarities reach their ultimate conclusion. It's not a surface, not a wall you could bump into. There's nothing physical there to feel under your hands. It's a mathematical threshold, a precise distance from the center of the black hole, where the escape velocity, the speed needed to get away from its gravity, matches the speed of light. That means that beyond this point, not even light can escape. And since light is our main tool for seeing and communicating across space, anything crossing that boundary is effectively cut off from the rest of the universe. For an astronaut or a spacecraft, the event horizon marks the moment when all paths lead inward. It doesn't matter how powerful your engines are, how much fuel you have, or what direction you aim. Once you cross it, every possible trajectory curves inward toward the center. There's no slowing down and hovering, no quick burst to reverse course. The geometry of space itself is bent so that every road points the same way, toward the singularity at the black hole's heart. From far away, you might think of it as a circle around the black hole, or a sphere if you're picturing it in 3 dimensions. In reality, its exact shape can be influenced by rotation and other factors, but the simplest case, the non-rotating, perfectly spherical black hole, is where the concept was first clearly understood. That's the Schwarzschild black hole, named after the German physicist Karl Schwarzschild, who, during World War I, worked out the first exact solution to Einstein's equations of general relativity that described such an object. His work showed that if you compress enough mass into a small enough volume, the curvature of spacetime becomes so steep that beyond a certain radius, escape is impossible. This radius is called the Schwarzschild radius, and for a non-rotating black hole, it's the distance from the centre to the event horizon. The size depends entirely on the black hole's mass. A black hole with the mass of our Sun would have an event horizon about 3 kilometers across. A supermassive black hole with millions or billions of solar masses, like the ones found at the centres of galaxies, can have event horizons millions of kilometers in diameter. But regardless of size, the principle is the same. Once you're inside, you're not coming back. Even so, it's worth pointing out that crossing the event horizon itself wouldn't feel dramatic to the person doing it. There's no sudden jolt, no flash of light or loud alarm. The local conditions might be perfectly calm, at least for a large black hole. You could drift across without realizing you'd passed the threshold. It's only the outside observer, someone watching from a safe distance, who would notice something strange. From their perspective, you would appear to slow down as you approach the horizon, your movements becoming sluggish, your signals taking longer and longer to arrive. The light from you would become redder, stretched by the intense gravity until it faded completely. To them, you'd never quite cross the horizon at all, just hover at its edge, fading into invisibility. This difference in perspectives is one of the most fascinating aspects of the event horizon. It's a direct consequence of how gravity affects time, something we'll spend more time on later. For now, it's enough to say that the event horizon isn't just about trapping objects in space, it's about trapping them in time as well. And here's the strange thing. While the event horizon is defined by physics that we can describe in detail, the region beyond it is almost entirely unknown to us. We can't observe it directly, not because it's hidden by material, but because the information simply can't get out. Whatever happens there stays there, making it one of the most mysterious regions in the universe. That doesn't mean scientists haven't tried to piece together what might occur inside. Theoretical models suggest some possibilities, but they remain speculative. The only certainty is that the laws of physics as we currently understand them are pushed to their limits inside. Even without knowing what lies beyond, the event horizon itself plays an important role in astrophysics. It defines the size of the black hole in a meaningful way. It influences the way matter falls in and the way energy is released from the surrounding region. And it helps determine what we can see when we look at a black hole from afar. Observatories like the Event Horizon Telescope use the light from matter just outside the horizon, swirling in what's called the accretion disk, to infer the shape and size of the black hole's shadow. This shadow isn't the event horizon itself, but it's closely related. From here, we can begin to move toward understanding what makes the event horizon so unique among cosmic boundaries, how it forms, and why its very existence challenges our ideas about space, time, and information. It's not just an edge, it's a test of our understanding of the universe's deepest rules, a place where theory and reality meet, in a way that forces us to think differently about everything from gravity to causality. And before we can explore those ideas in detail, we'll need to step back and understand how something as extreme as a black hole can even come into existence, and why nature makes them at all. A black hole does not announce itself with a flourish. There is no glowing sign in the darkness, no voice calling out across the cosmic void. Its presence is instead hinted at, revealed by what it does to its surroundings. In the vast expanse of space, where stars burn for billions of years and planets drift in slow orbits, a black hole is an almost perfect listener. It watches everything come near, and if something wanders too close, it simply keeps it. This is the quiet invitation it offers, an invitation that cannot be refused once accepted. From a distance, you could pass right by one without ever realizing it was there. The darkness between stars is full of places that contain nothing at all, and to the eye, a black hole is just another patch of that darkness. But the difference becomes clear if matter gets close enough to feel its pull. Gas, dust, and even light itself follow curved paths around it, paths determined not by invisible strings or forces tugging in the usual way, but by the bending of the space they move through. General relativity describes this as the curvature of spacetime, and in a black hole, that curvature is pushed to extremes. The word invitation might sound strange when we're talking about something so absolute and final, but that's because black holes don't grab things suddenly like a predator pouncing. Their reach is gradual. As you move closer, the influence grows stronger, and unless you have the energy to fight it, you will find yourself drifting in, drawn by the simplest law in the universe. Massive objects pull on other objects. This happens everywhere. Planets pull on moons, stars pull on planets. But near a black hole, the pull becomes irresistible at a certain point. Long before you reach the event horizon, you would notice the signs. For one thing, objects orbiting a black hole can move at incredible speeds. Around a normal star, there's a limit to how fast you can orbit without flying off into space or falling inward. Around a black hole, that balance point is shifted, and stable orbits can be frighteningly fast. Matter falling toward it doesn't simply drop, it spirals in, forming a flattened disk that circles at nearly the speed of light. This is the accretion disk, and it can be one of the brightest objects in the universe, outshining entire galaxies in some cases. That brightness isn't coming from the black hole itself. The hole remains invisible. It comes from friction and compression as matter in the disk rubs together, heats up, and emits radiation. Gas molecules slam into each other, speeding up and getting hotter until they glow with X-rays and gamma rays. It's a strange irony that one of the darkest objects in existence can be surrounded by such intense light. This light is, in a way, the first real sign of the black hole's presence, a warning to any wandering dust clouds or drifting asteroids that this is not a place to approach lightly. If you could hover at a safe distance and watch, you'd see the accretion disk as a warped ring of light. Gravity would bend the light paths around the hole so that you'd see not just the near side of the disk, but also the far side, wrapped upward and downward into view. This distortion makes black holes some of the most visually striking objects in astrophysics. Though capturing such images is a feat requiring telescopes the size of continents working together, even without such dramatic disks, a black hole's quiet invitation is still at work. It doesn't need a glowing halo to attract matter. A lone star wandering too close might be captured into orbit, eventually stripped of its outer layers. A passing cloud of gas might be stretched and funneled inward, each particle following the warped geometry toward the center. These processes can take thousands or millions of years, but the black hole is patient. The most intriguing part of this invitation is that it doesn't feel like a trap from the inside. Gravity is not a wall you crash into. It's a steady, constant influence. Imagine being in a spacecraft far from any planets or stars, and your engines fail. If you're within the sphere of influence of a black hole, you wouldn't notice anything sudden. Your trajectory would slowly begin to curve. The pull would grow stronger the closer you got, but there's no point where it suddenly changes from safe to dangerous. That point, the event horizon, is invisible and intangible. You'd only realize its significance if you tried to escape and found you couldn't. In a sense, the event horizon is just the black hole's way of defining the final limit of that invitation. It's not a place of violence. In fact, for a sufficiently large black hole, crossing it might feel no different than drifting through empty space. If the black hole is supermassive, millions or billions of times the mass of the Sun, the tidal forces at the horizon can be surprisingly gentle. You wouldn't be torn apart immediately. You could cross in silence, unaware that every possible future now leads inward. This gradual nature is part of why black holes have such a strange place in science. They are not violent in the way explosions or supernovae are. Those are events you can point to and say, there, it happened. A black hole is simply a region of space where the geometry has been shaped in such a way that nothing can leave. It can sit for millions of years, undisturbed, occasionally feeding on passing matter but otherwise silent. When black holes do feed, The process is as revealing as it is extreme. Astronomers studying X-ray emissions from distant galaxies can often identify the signature of matter spiraling toward an event horizon. These emissions come from the last stable orbits before the point of no return. They tell us about the spin of the black hole, the amount of mass it has, and even hint at the shape of spacetime in its immediate vicinity. All of this comes from the light released by material that is about to disappear forever. And yet, for all its drama, the idea of an event horizon is grounded in a simple concept: escape velocity. Every massive body has one. The Earth's escape velocity is about 11 kilometers per second. A neutron star's is much higher, a fraction of the speed of light. For a black hole, the escape velocity at the horizon equals the speed of light exactly. Light has no mass, but it does have energy, and gravity affects it just as it does everything else. If light cannot escape, nothing else can either. That is the core of the black hole's quiet certainty. It's easy to imagine black holes as devouring anything nearby, but in truth they don't pull in matter any more aggressively than a normal object of the same mass. If our sun were replaced by a black hole of equal mass, the planets would continue orbiting exactly as before. We wouldn't be drawn in unless we moved closer. The difference is that once something does fall in, it doesn't come out again. The invitation, once accepted, is permanent. From the perspective of the universe at large, black holes are not rare. They're formed when massive stars collapse at the end of their lives, and over cosmic time, galaxies can contain millions of them. Some are small, formed from a single stellar collapse. Others are giants at the centres of galaxies, grown by swallowing stars, gas, and smaller black holes. Each one has its own event horizon. Each one offers its own silent path inward. The real fascination comes from what this all means for our understanding of space and time. An event horizon isn't just a location in space. It's a boundary in the very fabric of reality. Cross it, and your place in the universe is redefined. You're now in a region where the future is singular, where all paths lead to the same endpoint. No amount of force can change that, because the space itself is shaped to make it inevitable. This is the part of the black hole's invitation that is both unsettling and captivating. It doesn't care what you are: light, matter, energy. It doesn't even require that you move toward it under your own power. The space you occupy will carry you along, and the closer you get, the more the normal rules of perspective, time, and distance begin to change. The view of the outside world narrows, the flow of time shifts, and the geometry itself becomes distorted. As we move deeper into the discussion, this quiet pull toward the horizon will become more than just a matter of gravity. It will lead us into the strange interplay between light and darkness, between what can be seen and what is forever hidden, and between the laws of physics as we know them and the mysteries that still remain unsolved. The event horizon is not just the edge of a black hole, it's the edge of our understanding, and beyond it lies a place where every theory we have might need to be rewritten. The closer you are to a black hole, the more you begin to appreciate just how relentless gravity can be. On Earth, it's an everyday companion, steady and predictable, holding your feet to the ground and shaping the motion of the oceans. Around our sun, it guides the planets along their orbits, keeping them in a delicate balance between falling inward and moving forward. But the gravity of a black hole is different, not because the law itself changes, but because it's taken to its logical extreme. There's no gentle balance once you've crossed a certain threshold. The pull doesn't just keep you nearby, it brings you in, and it doesn't let you go. Gravity has no personality, no will of its own, yet when you stand back and look at its effects on the larger scales, it can feel like a kind of hunger. It is the one interaction that never pushes away, never turns off, never saturates. You can shield yourself from heat with insulation, block light with walls, avoid collisions with careful planning, but there's no hiding from gravity. It acts across infinite distances, getting weaker with space but never truly disappearing. And with black holes, that quiet persistence is taken to a place where its grip becomes absolute. What makes a black hole's gravity so extreme is not its strength at a distance. It obeys the same inverse square law as any other object, but the way mass is concentrated into such a small region. For most familiar objects, you can't get close enough for gravity to become overwhelming. The Earth's surface keeps you far from its centre. Even a neutron star, dense as it is, still has a measurable radius that prevents you from getting too close to where its pull would be irresistible. But a black hole's mass is compressed to a point, or at least to a region so small that our current theories can't describe it in detail. That means you can approach far closer to the centre of mass than with any other object, and that's where gravity reveals its most extreme behaviour. If you were falling toward a black hole, you wouldn't necessarily feel anything unusual at first. Your motion would be smooth, dictated by the curvature of space itself. The sensation of being pulled in comes not from some external tug, but from the way your path through space-time is being guided. And if the black hole is massive enough, the change in gravity across your body, the tidal force, would be small at first, perhaps small enough that you wouldn't notice it at all. But as you continued inward, the differences in pull between your feet and your head would grow sharper. For smaller black holes, those differences become violent much sooner, stretching you along one axis while compressing you along another. This process has an uncomfortably descriptive name: spaghettification. The hunger of gravity in a black hole is different from the kind that swallows matter in everyday life. Here on Earth, when something falls, it can be stopped. A ball can hit the ground, a meteor can burn up in the atmosphere, an object can hit a wall. A black hole offers no such surface. The inward motion has no interruption because there is no place to land. Even before crossing the event horizon, the space around a black hole is so curved that escaping requires enormous energy. The closer you are, the more energy you need. At the horizon itself, the requirement becomes infinite if you hope to move outward. That's why light, the fastest thing in the universe, cannot get away once it's crossed that line. You can think of the surrounding space like the slope of a hill. Far away from the black hole, the hill is shallow and it's easy to move away if you choose. Closer in, the slope steepens, and it takes more and more effort to climb out. At the event horizon, the slope becomes vertical and no climb is possible. Inside, the slope turns over completely, and all paths, no matter which way you point, lead downward toward the centre. This is the geometry that gravity creates when mass is compressed beyond a certain limit, and it's that geometry, not some mysterious force, that pulls everything in. This endless hunger is not about rapid consumption. Black holes can and do go for long periods without actively feeding. In fact, if nothing passes close enough to be captured, they remain invisible and inactive, blending into the dark background of space. But when matter does come near, the transformation is remarkable. As it spirals inward, it releases gravitational energy, heating up and emitting radiation in quantities that can rival or surpass the light from an entire galaxy. This radiation comes from the material before it crosses the horizon. Once inside, there's no more light to be seen. Some black holes, especially the ones at the centres of active galaxies, feed on a nearly continuous supply of gas and dust. The process is not smooth but chaotic, with clumps of matter colliding and heating in turbulent patterns. In some cases, the energy release can drive powerful jets, streams of charged particles accelerated to nearly the speed of light, that shoot out along the black hole's rotational axis. These jets can extend for thousands of light years, influencing the formation of stars and the structure of the galaxy around them. Ironically, this means a black hole's appetite can shape the environment far beyond its immediate reach. On smaller scales, stellar mass black holes formed from collapsed stars often feed sporadically, drawing in material from a companion star if one is nearby. The material forms an accretion disk, just as with supermassive black holes, but the scale is smaller and the feeding is intermittent. When these systems flare, the X-rays they emit can be detected across vast distances, allowing astronomers to pinpoint their location. These flares are the signature of gravity at work, converting mass into energy with far greater efficiency than any process we can replicate on Earth. What's remarkable is that despite the intensity of these processes, the black hole itself remains unchanged in one respect. It doesn't have a surface to erode, no outer layer to strip away. Everything that falls in simply adds to its mass, making the event horizon larger and its gravitational influence stronger. The more it consumes, the greater its reach, and yet the process is silent from the black hole's side. The noise, the light, the turbulence, all of that happens outside the horizon, in the surrounding space where matter still has the freedom to interact. This is why scientists often say that black holes are simple in their final form. According to the no-hair theorem in physics, a black hole can be fully described by just a few properties: its mass, its electric charge, and its spin. The details of what fell in, the shape of a star, the arrangement of atoms, the structure of a planet, are lost from the outside perspective. Gravity doesn't care about the particulars. It treats every kilogram of mass the same way, whether it comes from a cloud of gas or a fragment of a comet. That uniformity is part of why the event horizon feels like such a sharp boundary. Everything inside is reduced to the same final state, stripped of its history. Of course, this raises deep questions about whether information is truly lost when it crosses the horizon, and that's a problem physicists have been wrestling with for decades. But even without diving into the quantum puzzles, the classical view of gravity here is already a powerful one. The hunger is endless because the process has no built-in limit. As long as matter and energy exist nearby, the black hole will continue to grow. There's no saturation point, no point at which it's full. The only thing that can stop the growth is the absence of anything left to consume. That absence is rare in the crowded environments where black holes are often found. In galactic centers, there's always a supply of drifting gas, wandering stars, or debris from cosmic collisions. Even in quieter regions, a black hole might eventually encounter something to pull in. And on the larger scales, as galaxies merge and interact, their central black holes can find themselves in new feeding grounds, surrounded by fresh material to draw in. It's worth remembering that this process, for all its finality, is not unique to black holes. Every massive body in the universe has its own form of gravitational appetite. Planets collect moons, stars gather planets, galaxies pull in smaller galaxies. What sets black holes apart is that their appetite has no point of refusal. Once something crosses the horizon, there is no negotiation, no chance to change course. That certainty is what makes the event horizon such a profound concept. It's the ultimate expression of gravity's pull, where escape is no longer part of the equation. As you picture this, it's important not to imagine the process as violent in every case. For a supermassive black hole, you could cross the horizon without feeling a sudden change. The tidal forces might be mild enough that your body, your spacecraft, even your instruments remain intact for some time afterward. The destruction comes later, closer to the singularity itself, where the curvature of space becomes extreme. The hunger here is not about speed but inevitability. You can fall slowly or quickly, but the destination is always the same. From the outside, though, the story looks very different. An observer far from the black hole would see you slow as you approach the horizon, your signals taking longer to arrive, your image growing dimmer and redder. They would never see you cross the line. To them, it would seem as though you were forever approaching, frozen at the edge. In this way, gravity's hunger is not just about pulling things in. It's about reshaping how reality is perceived depending on where you are. When people first hear the term black hole, it's natural to picture a kind of hole in space, a pit that things fall into. The truth is more subtle and stranger. What we're really talking about is a region where space-time itself is shaped in such a way that every possible path leads inward. Calling it a trap isn't wrong, but unlike a snare or a cage, it has no physical walls, no surface you can run into, no visible edges in the traditional sense. It is the geometry itself that becomes the mechanism of capture. To picture it, you might start by imagining the gravitational pull of a planet or a star. Far away, the space around them is almost flat. Light and objects can move in nearly straight lines. As you get closer, those lines bend, curving toward the mass. For ordinary objects, that curvature never becomes steep enough to force every path to end at the center. You can orbit, or you can escape entirely if you have enough speed. With a black hole, the curvature grows so extreme that beyond a certain radius, the event horizon, there are no outward paths left. That radius depends on the mass of the black hole. For a non-rotating one, it's defined by the Schwarzschild solution to Einstein's equations. Double the mass and the radius doubles as well. In the simplest form, the structure has just two main parts, the event horizon itself and the singularity at the center. But in reality, there's more to the anatomy of this cosmic trap than just an inner point and an outer limit. There's the surrounding space where light and matter behave in unusual ways, the possible presence of an ergosphere in rotating black holes, the photon sphere where light can orbit in circles, and the accretion disk where infalling material announces the black hole's presence to the rest of the universe. If you could map the gravitational influence of a black hole, the first striking feature you'd encounter moving inward from far away is the photon sphere. This is the distance from the center where light itself can orbit the black hole in a perfect circle. For a Schwarzschild black hole, this happens at 1.5 times the Schwarzschild radius. It's not a safe place to be. Those orbits are unstable. A tiny push inward or outward will send light either spiraling into the black hole or escaping into space. But it's an important part of the structure, because it's here that gravity has become strong enough to make the fastest thing in the universe loop around instead of flying off. Closer in is the event horizon. It's tempting to think of it as a kind of invisible membrane. In fact, if you plotted it on a diagram of spacetime, it's more like the outer edge of a funnel that narrows toward the singularity. Once you cross it, you can't get back out, not because something is pulling you down in the usual sense, but because the geometry has turned inward in every possible direction. Even if you pointed your engines straight up and fired them at full power, the space you're moving through would still be carrying you toward the center. Inside the event horizon, the paths through space are radically altered. In normal space-time, you can choose your direction, forward, backward, up, down, or any combination. Inside the horizon, the coordinate that we think of as time and the one that measures distance to the center swap roles in a sense. Moving inward is as inevitable as moving forward in time. Just as you can't decide to stop moving into the future, you can't decide to stop moving toward the singularity. This is one of the most counterintuitive consequences of the black hole structure, and it's a direct result of how Einstein's equations describe gravity not as a force, but as the curvature of space-time itself. The singularity is the ultimate center of the black hole, the place where the curvature becomes infinite according to classical general relativity. It's not a point you can reach in a meaningful physical sense, because the very concepts of space and time break down there. Our current theories don't tell us what's really inside. A quantum theory of gravity would be needed to answer that. But in the classical picture, the singularity is where all the paths that cross the horizon end. It's the terminus of the trap, the point from which nothing returns. For rotating black holes, the anatomy is more complex. Rotation drags space-time around with it, a phenomenon called frame dragging. This creates an outer region called the ergosphere, shaped somewhat like a flattened sphere that bulges at the equator. Inside the ergosphere, but outside the event horizon, objects can still escape, but they can't remain stationary relative to distant observers. They're forced to move in the direction of the black hole's spin. The ergosphere is interesting because it allows for something called the Penrose process, a theoretical way to extract energy from a rotating black hole. In this process, an object entering the ergosphere can split. with one part falling into the black hole and the other escaping with more energy than it started with. This doesn't violate any laws of physics. It draws that energy from the rotation itself. Surrounding all of this is the region where the black hole's gravity dominates, but isn't yet absolute. It's here that you find the accretion disk if there's material falling in. The disk can be blisteringly hot, producing X-rays and gamma rays, and it can be turbulent, with magnetic fields twisting through it. This is the part of the black hole that we can detect directly, the place where matter still interacts with the rest of the universe, before disappearing past the horizon. In some systems, jets of material erupt from the poles, powered by the complex interplay between magnetic fields, the accretion disk and the black hole's rotation. These jets can travel for thousands or even millions of light years, influencing the structure of entire galaxies. It's worth noting that in the standard picture, nothing material exists at the event horizon itself. It's not made of matter, it's a boundary in spacetime. You could cross it without bumping into anything solid. From your own perspective, nothing unusual would happen at that exact moment, unless the black hole is small enough for the tidal forces to be extreme right there. But to an outside observer, that crossing would never be seen. They would watch you approach more and more slowly, the light from you shifting to redder wavelengths until it fades away entirely. This difference in viewpoints is built into the geometry of the trap. The outside perspective is shaped by the way light climbs out of the gravitational well, losing energy and stretching in wavelength. The inside perspective is shaped by the way time and space are redefined by the curvature. Both are correct within their own frames of reference, but they don't match each other. This is one of the reasons black holes are so fascinating. They force us to accept that reality can look completely different depending on where you stand. All of these layers, the photon sphere, the event horizon, the singularity, the ergosphere in rotating cases, and the surrounding accretion structures, make up the anatomy of a black hole's trap. Each part has its own role in how the black hole interacts with the universe. Some are visible through the effects they have on light and matter. Others are purely theoretical boundaries that follow from the mathematics of relativity. Together, they form a coherent picture of how something can exist in the universe that is at once invisible and yet impossible to hide from, silent and yet capable of outshining galaxies through the violence it creates outside its boundaries. Understanding this anatomy is not just about curiosity. It's about recognizing that the event horizon is not a magical line, but a natural outcome of the way gravity works when taken to its extremes. Every layer of the structure can be described in terms of the same physical principles that keep planets in orbit and guide spacecraft through the solar system. The differences in the scale and the concentration of mass. In a sense, a black hole is what you get when you keep turning up gravity's intensity without changing the rules, until the structure of spacetime itself is reshaped into a one-way funnel. When scientists today talk about black holes, they speak with a certain level of confidence. We have direct images of their shadows, measurements of the gravitational waves they produce when they merge, and decades of observational evidence showing their influence on nearby stars and gas. But that wasn't always the case. For a long time, black holes existed more in thought experiments than in telescopes, as curiosities hidden in the mathematics of gravity. They were strange solutions to equations that even many physicists doubted could represent anything in the real universe. The earliest roots of the idea go back much further than Einstein, or even the word black hole. In the late 18th century, long before the discovery of general relativity, a few thinkers began wondering about what would happen if an object's gravity became so strong that not even light could escape. In 1783, an English clergyman and natural philosopher named John Michell wrote to the Royal Society describing what he called a dark star. He calculated that if a star were massive enough and compact enough, the escape velocity at its surface could exceed the speed of light. Since light was thought to have mass in the Newtonian framework of the time, it would be pulled back in, making the star invisible. Just a few years later, the French mathematician Pierre-Simon Laplace independently describe the same concept, suggesting that there could be objects in the universe that no light could reach us from, rendering them undetectable except by their gravitational influence. These were intriguing ideas, but in the absence of a wave theory of light or any evidence for such extreme objects, they were more curiosities than serious astrophysical proposals. As physics advanced into the 19th century, with light understood as a wave rather than a stream of particles and no known mechanism for creating such dense masses, the dark star idea faded from serious discussion. The concept re-emerged in a very different form after Albert Einstein published his theory of general relativity in 1915. This new theory described gravity not as a force acting at a distance, as Newton had, but as the curvature of spacetime caused by mass and energy. In 1916, Karl Schwarzschild, serving on the Eastern Front during World War I, found the first exact solution to Einstein's field equations that described the gravitational field outside a spherically symmetric mass. His solution showed that if such a mass were compressed within a certain critical radius, the Schwarzschild radius, the curvature would become so extreme that not even light could escape. Schwarzschild himself didn't speculate much about whether such an object could exist in reality. At the time, most physicists assumed that the conditions needed to create one would never occur naturally. The singularity at the centre, where the equations predicted infinite curvature, was often seen as a mathematical artifact, a sign that the solution didn't apply there. The idea was interesting but set aside, partly because there were more pressing problems to explore in this new theory of gravity, and partly because nature seemed too stable and orderly to produce such extreme objects. For the next few decades, the concept of a black hole, though that term didn't yet exist, remained on the fringes of theoretical physics. Then, in the 1930s, work by Subrahmanyan Chandrasekhar on the fate of massive stars began to challenge the assumption that such objects were impossible. Chandrasekhar calculated that a star with more than about 1.4 times the mass of the Sun could not support itself against gravity once it exhausted its nuclear fuel. Lighter stars could become white dwarfs, supported by electron degeneracy pressure, but above that limit, the pressure would not be enough. At the time, this conclusion met strong resistance, most famously from Arthur Eddington, one of the leading astronomers of the day. Eddington argued that nature would surely find a way out to prevent such a catastrophic collapse. The idea that a star could collapse indefinitely was unsettling, and without observational evidence it remained speculative. But the mathematics didn't go away, and over time more theorists began to explore the implications. By the 1960s, developments in both theory and observation began to shift the conversation. On the theoretical side, work by physicists like John Wheeler, Roger Penrose, and Stephen Hawking began to show that under realistic conditions, gravitational collapse could indeed lead to the formation of an event horizon. Penrose proved that once a trapped surface, a region from which all light is moving inward, forms, the collapse will inevitably continue to a singularity, assuming general relativity holds. This was not an exotic or finely tuned scenario. It was a natural outcome of the theory for massive enough stars. Around the same time, observational astronomy was going through a revolution. The advent of radio telescopes, X-ray detectors, and more sensitive optical instruments was revealing a universe far more violent and energetic than previously imagined. In 1964, astronomers discovered Cygnus X1, a powerful X-ray source in our galaxy. Further study suggested that the source was a massive invisible companion to a bright star, too massive to be a neutron star, and best explained as a black hole. This was one of the first strong pieces of evidence that black holes were not just theoretical constructs, but real astrophysical objects. It was in this era that John Wheeler popularized the term black hole, a name that captured both the defining feature of these objects, their inability to let light escape, and the mystery surrounding them. The term stuck, and with it came a surge of public and scientific interest. black holes began to appear in science fiction stories, magazine articles, and eventually in high-profile observational campaigns. The 1970s and 80s saw the development of more detailed models of how black holes interact with their environment. Astronomers studied the accretion disks that form as matter spirals in, the powerful jets that some black holes launch, and the effects of their gravity on nearby stars. The idea of supermassive black holes at the centres of galaxies began to take hold, supported by evidence from the motion of stars and gas in galactic nuclei. The quasar phenomenon, extremely bright and distant sources powered by accreting black holes, became a key piece of the puzzle. By the late 20th century, black holes had moved firmly into the mainstream of astrophysics. They were recognised not as rare oddities, but as important players in the evolution of galaxies and the large-scale structure of the universe. Observations with the Hubble Space Telescope and other instruments confirmed the presence of supermassive black holes in many, perhaps most, large galaxies, including our own Milky Way. The motions of stars near the galactic centre pointed to a compact object, millions of times the mass of the Sun, later imaged indirectly through radio observations as Sagittarius A. The 21st century has brought even more compelling evidence. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from the merger of two black holes, a signal that matched predictions from general relativity with remarkable precision. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow in the galaxy M87, a ring of light bent by gravity around a dark centre. These achievements confirmed in direct ways what decades of theory had suggested. The event horizon is not just a mathematical boundary, it's a real feature of the cosmos, and we can detect its presence. This history is a reminder of how science often works. Ideas can lie dormant for centuries, dismissed as curiosities, until new theories and technologies bring them back into focus. The path from Michel's dark stars to the image of M87's shadow was not a straight line, but a gradual weaving together of theory, mathematics, observation, and sometimes heated debate. The curiosity about what happens when gravity becomes overwhelming never quite went away. It just waited for the right tools to turn speculation into evidence. And now that we have those tools, the focus has shifted from asking whether black holes exist to exploring what they can teach us about the nature of space, time, and matter under extreme conditions. The event horizon, once an abstract concept, is now something we can study indirectly through the motion of stars, the glow of heated gas, and the patterns of radiation escaping from just outside its boundary. What was once an idea confined to letters written in the 18th century has become a cornerstone of modern astrophysics, influencing everything from our understanding of galaxy formation to the search for a theory that unites general relativity and quantum mechanics. Light has always been our most faithful messenger. From the glow of a candle to the faintest flicker from a galaxy billions of light years away, it is how we see, measure, and understand almost everything beyond our immediate reach. In space, there is no sound to carry over vast distances, no breeze to convey a scent or a touch. Light is the language of the universe, and our telescopes are the translators. But when light comes close to a black hole, that language becomes distorted, bent, and in the case of the event horizon, silenced altogether. The relationship between a black hole and light is unlike anything we encounter in everyday life. On Earth, light travels in straight lines unless it's reflected, refracted, or scattered by matter. Around a black hole, there doesn't need to be any matter for light to change its path. The space-time itself is curved, and light, which always moves along the straightest possible path in that curved geometry, follows those curves. This bending is not a trick of perspective. It is the direct result of gravity affecting the very stage on which light moves. Far from a black hole, this bending is subtle. The light from a distant star passing near a black hole might be deflected slightly, a a phenomenon known as gravitational lensing. This effect isn't unique to black holes. Massive galaxies and galaxy clusters can also bend light in this way. But as you move closer to a black hole, the bending becomes extreme. At a specific distance, light can orbit the black hole in a perfect circle. This is the photon sphere, a precarious ring where even the smallest nudge inward or outward will send the photon either spiraling in toward the horizon or escaping back into space. The photon sphere is not the same thing as the event horizon. Light at the photon sphere still has a chance to escape, but the orbits there are unstable. It's like balancing on the tip of a knife. Possible in theory, but any disturbance changes the outcome completely. If you could somehow stand outside the photon sphere and look in, the bending of light around the black hole would let you see the far side of anything near it. The light from the back side would be curved over the top and bottom, creating a distorted image. This warping is part of what makes simulated images of black holes so striking. A glowing ring of light that wraps around, showing multiple perspectives at once. As light gets closer to the event horizon, the bending becomes so strong that its path curves inward no matter which way it started. The horizon is the ultimate cutoff. Beyond it, all possible paths lead inward. From the inside, even a beam of light aimed directly outward will still end up at the singularity. This is why nothing inside can be seen from the outside. The light that would carry information about the interior can never reach us. From the point of view of an outside observer, light emitted by something falling toward the horizon behaves in an unusual way. As the object approaches, each photon it emits has to climb out of a deeper and deeper gravitational well. In doing so, the light loses energy, which shows up as an increase in wavelength. This is gravitational redshift. For visible light, it means the colour shifts toward the red end of the spectrum. For other wavelengths, it means moving toward the lower energy part of the electromagnetic range. As the source gets closer to the horizon, this redshift becomes extreme, pushing the light beyond the range of any possible detection. At the same time, the apparent rate at which the photons arrive changes. To the outside observer, the clock of the falling object seems to slow down as it nears the horizon. The intervals between photons grow longer, and the object appears to freeze in place, fading into darkness. This isn't because the object has actually stopped. It continues inward at full speed from its own perspective, but because the geometry of space-time stretches the path of the light and the time between its departure from the object's frame. For the object itself, there is no such slowdown. From its perspective, light behaves normally until the moment it crosses the horizon, after which there is no way to send any more messages out. This difference in perspectives, one seeing a fade and freeze, the other seeing a normal crossing, is a defining feature of the event horizon, and is rooted in the fact that time and space are not absolute, but relative to the observer. In rotating black holes, the interaction between light and gravity becomes even more complex. The spin drags space-time around with it, an effect called frame dragging. Light travelling in the direction of the spin can get closer to the horizon before being captured than light moving against the spin. This asymmetry affects the shape of the shadow we would see if we look directly at the black hole's silhouette against a glowing background. The Event Horizon Telescope's image of the black hole in M87 shows this effect subtly. The ring of light is not perfectly uniform, and the brightness varies depending on the direction of rotation and the distribution of material in the accretion disk. The bending of light near a black hole is not just a curiosity, it's one of the key ways we can detect and study them. When black holes pass in front of background stars, the gravitational lensing can cause the star to temporarily brighten as its light is focused toward us. This method, called microlensing, has been used to detect isolated black holes that are not actively feeding and are otherwise invisible. By measuring the way the light changes over time, astronomers can estimate the mass of the lensing object and determine whether it fits the profile of a black hole. Another way light reveals a black hole's presence is through the radiation emitted by material in the accretion disk. This light is often shifted in frequency both by the high speeds of the material, causing Doppler shifts, and by the gravitational field. The result is a broadened spectrum that tells us about the disk's rotation, the black hole's spin, and the strength of gravity just outside the horizon. The very shape of the spectrum becomes a kind of fingerprint for the conditions in that extreme environment. It's worth noting that while the event horizon represents a complete loss of contact for light, the influence of the black hole on light extends much farther out. Photons passing near it, but not falling in, can still have their paths bent dramatically, creating arcs, rings, and multiple images of background objects. In some cases, this lensing can magnify distant galaxies, letting us study structures that would otherwise be too faint to see. Black holes, in this way, can serve both as destroyers of light and as tools for revealing more of the universe. The interplay between light and darkness here is not a battle, but a relationship defined by the rules of spacetime. Light always travels along the paths available to it, and near a black hole those paths are shaped into curves that can circle, spiral, or terminate inward. There is no violation of the speed of light limit. Light always moves at the same speed locally, but the space it moves through is not flat, and that makes all the difference. This is why, in the end, a black hole's darkness is not simply the absence of light. It is the absence of paths for light to take outward. That absence is absolute once the horizon is crossed. Everything we know about black holes from observation comes from the light and other radiation produced outside that boundary. The shadow, the jets, the glowing disk. These are all phenomena of the outer regions, made visible by light that still has a way to reach us. Understanding how light behaves near a black hole not only gives us a way to detect these objects, but also a way to test the limits of general relativity. Every observation of light bending, every measurement of gravitational redshift, every mapping of a black hole's shadow is a chance to compare theory with reality. So far, the match has been remarkably close, but these are still early days in our ability to look at the most extreme gravitational fields in the universe. Following light's path to the horizon inevitably leads us to think about what lies at the boundary itself. The event horizon may be invisible, but its role is central. It marks the point where every possible beam of light is bent inward, where every outward path is erased from the map of space-time. When most people imagine the event horizon, they picture a perfect sphere, a simple, clean surface surrounding a black hole like the skin of an invisible bubble. That picture isn't entirely wrong, but the reality depends on the nature of the black hole itself. The event horizon's shape is dictated by mass, spin, and in theory even electric charge, though in practice astrophysical black holes are expected to have almost no net charge. In its simplest form, for a non-rotating black hole, the event horizon is indeed perfectly spherical, centered on the singularity, with every point on its surface at the same distance from the center. But nature rarely deals in perfectly simple cases. The easiest place to start is with the Schwarzschild black hole, the idealized non-rotating case described by Carl Schwarzschild's 1916 solution to Einstein's field equations. Here, the event horizon is defined by the Schwarzschild radius, a fixed distance from the singularity determined entirely by the black hole's mass. For such an object, the symmetry is perfect. No matter which direction you approach from, the distance to the horizon is the same. The geometry of the surrounding spacetime is spherically symmetric, meaning there's no preferred direction, no distortion, no flattening or bulging. This simplicity is part of why the Schwarzschild solution is the starting point in most discussions. It's the clean baseline before real-world complications enter the picture. But the universe doesn't just give us non-rotating black holes. Stars rotate, galaxies rotate, and when a massive star collapses into a black hole, it usually carries angular momentum with it. That spin becomes an intrinsic property of the resulting black hole. Once spin is introduced, the symmetry changes. The solution to Einstein's equations in this case is the Kerr metric, named after Roy Kerr, who discovered it in 1963. In the Kerr black hole, the event horizon is still a closed surface, but it's not perfectly spherical anymore. Rotation drags spacetime around with it, especially near the black hole. This effect, called frame dragging, means that the horizon is flattened slightly at the poles and bulges at the equator. The faster the black hole spins, the more pronounced this distortion becomes. In extreme cases, the radius of the horizon at the poles can be significantly smaller than at the equator. The difference isn't visible in any direct sense. After all, the horizon itself is invisible, but it shows up in the equations that describe the distances and shapes involved. For a maximally rotating Kerr black hole, something else happens as well. The event horizon moves inward compared to the non-rotating case, allowing stable orbits to exist closer to the singularity. Just outside the horizon is the ergosphere, a region where frame dragging is so strong that nothing can remain stationary relative to distant observers. The ergosphere's boundary at the equator lies outside the horizon, while at the poles it touches it. This teardrop-like distortion is one of the clearest signs that spin changes the shape of the structures surrounding a black hole. If we add electric charge into the mix, we get the Reissner-Nordström solution for non-rotating charged black holes, or the Kerr-Newman solution for rotating charged ones. In these cases, the horizon's position is altered again, but the idea of a large charge in an astrophysical black hole is mostly a theoretical curiosity. Any significant charge would attract opposite charges from the surrounding plasma, quickly neutralizing it. Still, in principle, the presence of charge changes the size and shape of the horizon in predictable ways, sometimes producing two horizons, an outer and an inner, though only the outer one serves as the point of no return for distant observers. All of this raises an important point. The event horizon is not a physical surface in the traditional sense. There's nothing there to touch, no barrier to bump into. It's a mathematical boundary defined by the paths that light and matter can take. If you crossed it, you wouldn't find yourself moving through a skin or membrane. You'd simply pass into a region where every possible path leads inward. From the inside, there's no obvious mark showing where you crossed. The shape exists in the geometry of spacetime itself, not in any material sense. Despite being intangible, the horizon's shape has practical consequences for the way a black hole interacts with its surroundings. In rotating black holes, the bulging equator and the presence of the ergosphere influence the dynamics of the accretion disk and the launching of jets. Magnetic fields anchored in the disk can thread through the ergosphere, tapping into the black hole's rotational energy through processes like the Blandford-Zanaek mechanism, powering some of the most energetic outflows in the universe. The geometry dictates not just where the horizon lies, but how the surrounding space can channel energy and matter. Observationally, we don't see the event horizon directly. We see its shadow, the dark area against the background of light from infalling material. This shadow is larger than the horizon itself because it's defined by the photon sphere, where light paths are bent into unstable orbits before escaping or falling inward. The shadow's apparent shape depends on the black hole's spin and our viewing angle. For a non-rotating black hole viewed face-on, the shadow is a perfect circle. For a rotating one, it can appear slightly compressed on one side, an effect caused by the way light is bent differently in the direction of the spin versus against it. The event horizon telescope's image of the black hole in M87 shows a remarkably circular shadow, suggesting that its spin, while significant, is not extreme from our viewpoint. It's easy to assume that once you know the black hole's mass and spin, you've fully described the shape of its horizon. And in general relativity that's true. Thanks to the no-hair theorem, the external properties of a black hole are completely determined by those quantities, and charge, if any. This simplicity is striking given how complex the processes that form black holes can be. Two black holes with completely different histories can end up with identical horizons if their mass and spin match. That uniformity means the event horizon is not a reflection of the details of what fell in, but of the fundamental parameters that define the black hole. One curious aspect of the horizon's shape is how it exists in the context of time. From a distant observer's point of view, the horizon is static for a stable black hole. It doesn't ripple or fluctuate visibly. But from the black hole's perspective, it can grow when new mass crosses it, a change that's irreversible according to classical general relativity. This leads to what's known as the area theorem, first proposed by Stephen Hawking. The total surface area of event horizons in the universe can never decrease. When two black holes merge, the area of the resulting horizon is always greater than the sum of the two originals. This idea has deep connections to thermodynamics, with the horizon's area acting like an analogue to entropy. That connection between geometry and thermodynamics is one of the most surprising outcomes of studying the horizon shape. It suggests that the surface area, while not physical in the usual sense, carries information about the black hole's internal state, or at least about its energy content. In the 1970s, Jacob Bekenstein proposed that a black hole's entropy is proportional to its horizon area, and Hawking later showed that black holes can emit radiation, slowly shrinking over incredibly long timescales. In this picture, the shape and size of the horizon are tied to deep questions about the nature of information, quantum mechanics, and gravity. Even though we can't see the event horizon directly, our ability to measure its effects has grown dramatically. The size of the shadow in the M87 image, the way stars orbit around Sagittarius A, the patterns in gravitational waves from black hole mergers, all of these are tests of the predictions about the horizon's geometry. So far, every observation is consistent with the shapes predicted by general relativity, even in the most extreme environments we can study. That consistency is both reassuring and frustrating. Reassuring because it confirms our best theory of gravity. Frustrating because it gives us no obvious hint of new physics. But in science, even a perfect match between theory and observation can be an invitation to look closer. Tiny deviations in the shadow shape, small differences in the timing of gravitational waves, subtle shifts in the way light bends. Any of these could hint at physics beyond general relativity. That's why the shape of the event horizon is more than just a curiosity. It's a place where the known laws of physics are pushed to their limit, and where even a small discrepancy could open the door to entirely new ideas about space, time, and matter. Thinking about the shape of the horizon inevitably leads to thinking about what it's guarding. The horizon is the border, but the singularity inside is the ultimate destination for anything that crosses. The path from one to the other is governed by the structure of space-time itself, and the journey inward is shaped by the same gravity that defines the horizon's curve. When something drifts too close to a black hole, the pull it feels is not uniform. Gravity weakens with distance, so the part of the object nearer the black hole experiences a stronger attraction than the part farther away. Under ordinary circumstances, this difference is tiny and goes unnoticed, but near a black hole, especially a small or medium mass one, that gradient can become so steep that it stretches objects along the direction of the pull and compresses them from the sides. The result has been given a name that sounds almost whimsical, even though the reality is anything but spaghettification. It's a light-hearted term for a process rooted in the unyielding geometry of space-time. Imagine you are falling feet first toward a black hole. Your feet are slightly closer to the singularity than your head, so they are pulled more strongly. Even a tiny difference in distance translates into a measurable difference in force when the gravitational field is this intense. At the same time, the space around you is being curved inward, squeezing in the horizontal directions. These combined effects stretch you lengthwise and squeeze you sideways. In the extreme, this could turn any three-dimensional object into a long, thin filament before it crosses the event horizon. The severity of spaghettification depends heavily on the mass of the black hole. For stellar mass black holes, perhaps a few times the mass of the Sun, the tidal forces at the event horizon are enormous. Crossing that boundary would mean instant destruction for anything made of ordinary matter. atoms would be torn apart by the tidal differential before even reaching the singularity. In contrast, for a supermassive black hole, the size of the event horizon is much larger, and the gradient in gravity across the span of a human body, or even a spacecraft, is relatively mild at the horizon. You could, in principle, cross it without feeling anything unusual at that moment. The fatal stretching would occur deeper inside, closer to the singularity itself. The mechanics of spaghettification can be described in terms of tidal forces, which are simply differences in gravitational acceleration across an object. On Earth, tidal forces are most familiar in the form of ocean tides, where the moon's gravity pulls more strongly on the side of the planet facing it than on the far side. The difference is small, just enough to move vast amounts of water over the course of the hours. But the principle is the same whether you're talking about ocean tides or the stretching of an object near a black hole. The scale is what changes. Near a black hole, the gradient can be so steep that the difference in gravitational pull between your feet and your head is measured not in fractions of a millimetre per second squared, but in thousands or millions of times Earth's gravity. This stretching is not just a theoretical curiosity. Astronomers have observed events that appear to be tidal disruption events, where a star wanders too close to a black hole and is torn apart by these forces. In such a case, the star's material is pulled into a long stream, wrapping around the black hole and colliding with itself to form a temporary accretion disk. This process releases tremendous amounts of energy, often visible in ultraviolet, X-ray, and sometimes even visible light. The flare from such an event can outshine an entire galaxy for weeks or months before fading. On a smaller scale, anything that falls into a black hole, asteroids, comets, gas clouds, experiences the same principles. The object is stretched along its path of motion and compressed in perpendicular directions. This is not just a matter of being pulled apart like taffy. The compression in the other directions is just as extreme. In the language of general relativity, space-time near a massive body curves in such a way that geodesics, the natural paths of particles, converge in some directions while diverging in others. Near a black hole, the divergence along the radial direction and convergence in the tangential directions become extreme. From the perspective of the falling object, this process happens quickly once the tidal forces become strong enough. There is no pause or plateau. It accelerates as you get closer to the singularity. The equations describing free fall into a Schwarzschild black hole show that, from your own point of view, you reach the singularity in a finite amount of time after crossing the horizon. The stretching continues until every part of your body is moving along nearly parallel paths toward the same point, at which scale ordinary concepts of shape and size cease to apply. For supermassive black holes, as we said, the stretching is less dramatic at the horizon, but that doesn't mean it's absent. It just means it's delayed. You might have minutes, hours, or even days, depending on the mass, before the tidal forces grow overwhelming. During that time, the view of the outside universe would become more and more distorted. Light from behind you could be bent around, letting you see parts of the universe you would never see otherwise. Closer still, the distortions would be so extreme that the outside view would collapse into a thin, bright ring in the direction of the singularity, the rest of the sky smeared and warped by the curvature. If we step back from the visceral image of a human or object being pulled into threads, spaghettification has important implications for astrophysics. It's a direct consequence of the fact that space-time curvature is not uniform around massive objects. It's also one of the few processes near a black hole that can produce observable signals from an otherwise invisible interaction. Tidal disruption events, when they happen to stars, not only light up the black hole's surroundings, but also give us clues about the black hole's mass and spin. The light curves from these events, the way the brightness changes over time, can be modelled to estimate the properties of the black hole doing the stretching. In some rare cases, tidal disruption events have been observed to launch relativistic jets, beams of material moving at nearly the speed of light. These are thought to be powered by magnetic fields in the newly formed accretion disk, tapping into the energy of the infalling material and possibly the rotation of the black hole itself. Such events are windows into the physics of both gravity and high-energy astrophysics, offering a brief but intense opportunity to study environments we cannot recreate on Earth. What makes spaghettification such a compelling part of the black hole story is that it bridges the gap between the abstract and the tangible. The event horizon is a mathematical boundary. The singularity is a theoretical construct we can't observe directly. But the tidal forces that cause spaghettification are something we can describe, calculate, and in certain cases, watch unfold in real time. They are the physical manifestation of the black hole's geometry in action, a reminder that gravity is not just a passive shaping of space-time, but an active influence on anything caught in its pull. Of course, in the quiet vacuum of space, there is no sound to accompany the stretching, no tearing noise to announce what's happening. The process is silent, inevitable, and inescapable once you cross the point where the tidal forces dominate. If you were observing from a safe distance, you would not see the object elongate in real time, because the same gravitational time dilation that freezes the image of something at the horizon would also freeze the visible progression of the stretching. The final stages, where the object becomes a filament of atoms, would be hidden from your view, happening beyond the point of no return. This combination of invisibility and inevitability is part of what makes spaghettification such an evocative idea. It's a phenomenon we can describe with precise equations, simulate with computers, and even glimpse the indirect evidence of, yet it happens entirely beyond our ability to intervene or witness directly once the horizon is crossed. It is, in many ways, the perfect symbol of the black hole's nature, a process shaped by the immutable rules of gravity, hidden in the darkness, leaving only the faintest traces for us to study from afar. And yet, spaghettification is only one aspect of what happens as matter approaches the singularity. Beyond the stretching and compression, there is the fate of the information carried by that matter, the energy it releases as it falls, and the ways in which its journey might differ in the presence of rotation, magnetic fields, or quantum effects. Following the thread, quite literally, of what happens to something that falls in takes us deeper into the mysteries of black holes, where the known laws of physics meet the unknown. When Einstein first published his theory of general relativity in 1915, it rewrote the rules of how we understand gravity. Instead of being a force that acted across space, gravity became the shape of space-time itself. Objects followed the curves of this geometry, and those curves were determined by the distribution of mass and energy. The theory was immediately successful in explaining phenomena that Newton's law of gravitation could not, such as the subtle shift in Mercury's orbit and the bending of light by the sun's gravity during a solar eclipse. But one of the strangest consequences of Einstein's equations was not something he embraced. It was something he, in fact, seemed uneasy about. Not long after the equations were published, Carl Schwarzschild found an exact solution that described the space-time outside a spherical mass. The mathematics revealed something remarkable. If that mass were compacted into a radius smaller than a certain limit, the curvature of space-time would become so extreme that light could not escape. This critical radius came to be known as the Schwarzschild radius. Inside it, the equations implied all paths led inward to a singularity, a point where density became infinite and the known laws of physics broke down. Einstein acknowledged the solution, but he did not believe such objects could exist in nature. His reluctance wasn't unusual. Many physicists at the time thought the solution singularity was a sign of the theory's breakdown, not a description of a real physical object. The universe, in their view, was too well ordered to produce such pathological features. Collapse to infinite density seemed impossible, and the idea of a region from which nothing could escape was unsettling. For years, this skepticism persisted. Even Einstein himself published a paper in 1939, just months before the outbreak of World War II, arguing that the collapse of a massive star would be halted before a singularity could form. He suggested that quantum effects or other unknown physics would intervene to prevent such an outcome. In the same year, however, Robert Oppenheimer and Hartland Snyder published a paper that came to a very different conclusion. Using the framework of general relativity, they showed that a sufficiently massive star, once it exhausted its nuclear fuel, would undergo gravitational collapse that nothing could stop. To an outside observer, the star would seem to freeze and fade as it approached the Schwarzschild radius, but in its own frame, it would continue inward to a singularity in a finite amount of time. Oppenheimer and Snyder's work was theoretically sound, but the astronomical community didn't rush to embrace it. The war soon dominated the attention of much of the scientific world, and the collapse to a singularity was still seen as a mathematical oddity. It didn't help that there was no observational evidence to suggest such extreme objects existed. Stars were known, galaxies were known, but nothing like a black hole had been detected. Without data, the theory remained an elegant but speculative idea, easy to set aside in favour of more grounded research. Einstein's reluctance can be understood in part by looking at his approach to physics in general. He often sought theories that were elegant and complete, free of infinities and unresolved paradoxes. A singularity at the heart of a black hole was the opposite of that. It was a point where the equations of general relativity themselves broke down, a place where the theory stopped being able to make predictions. Such a feature, while mathematically possible, seemed to him like a sign that the theory was incomplete, missing some deeper principle that would smooth out the extreme behaviour. In the decades that followed, however, other physicists began to take the problem more seriously. In the 1960s, the work of Roger Penrose provided a turning point. Penrose developed powerful new mathematical tools to study the geometry of spacetime, showing that singularities were not just possible but inevitable under certain realistic conditions of collapse. This result didn't depend on perfect symmetry or special initial conditions. It applied to real stars with real imperfections. Penrose's singularity theorem made it clear that if general relativity was correct, gravitational collapse could and would produce singularities hidden behind event horizons. John Wheeler, another major figure in this period, helped bring the concept into the mainstream. He not only explored the theoretical properties of these objects, but also coined the term black hole in 1967, replacing more cumbersome phrases like gravitationally completely collapsed object. Wheeler's knack for clear, memorable language helped the idea gain traction both in the scientific community and in the public imagination. Still, acceptance was gradual. Even in the 1970s, some researchers viewed black holes with suspicion, considering them perhaps a useful approximation for certain phenomena, but not necessarily real astrophysical entities. Part of the challenge was that black holes were, by definition, invisible. The only way to detect one was through its influence on nearby matter or radiation. Early evidence came from X-ray astronomy, which revealed compact, massive objects in binary star systems, where a visible star was orbiting an unseen companion. The best explanation for some of these systems, like Cygnus X1, was that the invisible partner was a black hole. Even then, many scientists wanted more proof before they would concede that the most extreme predictions of general relativity had been realized in nature. Over time, that proof accumulated. Observations of quasars, extremely luminous galactic nuclei powered by accretion onto supermassive black holes, provided indirect evidence that such massive compact objects existed. Measurements of the orbits of stars near the centre of the Milky Way pointed to an invisible mass 4 million times that of the Sun confined to a region smaller than our solar system. By the 1990s, the case for black holes as real astrophysical objects had become strong enough that few in the field still doubted their existence. Yet it's telling that the path to this acceptance was slow, stretching over decades. It took a combination of theoretical breakthroughs, observational advances, and shifts in how physicists thought about space-time. Einstein's reluctance, and the similar hesitation of many of his contemporaries wasn't simply conservatism. It was a reflection of the fact that black holes are fundamentally unlike anything else in the universe. They represent the point where general relativity's smooth geometry gives way to a region we cannot describe without a new theory, likely one that unites relativity with quantum mechanics. Even today, while black holes are accepted as real, the singularity remains a mystery. Many physicists believe that a complete theory of quantum gravity will replace the singularity with something else, perhaps a region of extremely high but finite density, or a structure with entirely different properties. In that sense, Einstein's discomfort may have been justified, not in doubting the existence of event horizons, but in sensing that the picture we have is still incomplete. The reluctant acceptance of black holes in the scientific community is a reminder that new ideas, even when they emerge from our best theories, often need time and evidence to take root. It's also a reminder that physics is as much about asking questions as answering them. The questions that troubled Einstein, the nature of singularities, the fate of matter inside the horizon, the ultimate limits of relativity, are still active areas of research today. Understanding this history of doubt and gradual acceptance gives us perspective on the current frontiers. Just as Einstein and his peers wrestled with the reality of black holes, we now wrestle with the puzzles they still present. And to tackle those puzzles, we often return to the heart of the matter, the singularity itself, the place where everything that crosses the event horizon is destined to arrive, and the place where our understanding stops. At a certain distance from a black hole, there is a place that divides two entirely different realities. From one side, it is possible to escape. From the other, it is not. This place has no walls, no physical surface, no texture to brush against as you pass through. You could not see it if you were falling toward it, and yet its position is precise, defined by the mathematics of spacetime itself. This is the event horizon, the silent boundary between here and gone. It is called a horizon because, like the one we see on Earth, it marks the farthest point from which signals can reach us. But unlike the Earth's horizon, which recedes as you move toward it, the event horizon is fixed in place relative to the black hole. Once you cross it, you can no longer send a message back out, no matter how fast you try to move or how powerful a signal you use. The speed of light is the ultimate limit, and inside this boundary even light is drawn inward. From the outside, the event horizon is a surface of no return. If you imagine space-time as a kind of flowing fabric, the horizon is where the flow becomes so fast that it exceeds the speed of light. It is not that you are being pulled in by a force in the usual sense. Rather, the space itself is moving inward faster than light can move outward. The image often used is that of a waterfall. Outside the horizon, the current is swift but escapable. At the horizon, it matches the maximum speed possible. Beyond it, the current is faster than any attempt to swim against it. If you were watching an object fall toward the horizon from a safe distance, the scene would be strange. The closer the object gets, the more its light is redshifted. Each photon it emits must climb out of a deeper gravitational well, losing energy in the process. To you, this shows up as a shift toward longer wavelengths and lower frequencies. At the same time, the object's apparent motion slows. It never quite seems to reach the horizon. Instead, it appears to freeze, fading into darkness as the light stretches beyond the range of your detectors. This is not what the falling object experiences. From its own perspective, the crossing is uneventful. There is no sudden jolt, no visible boundary. It continues to move forward, and the horizon passes without ceremony. The only noticeable change is in the view of the outside universe, which becomes increasingly compressed and distorted. Light from all directions bends toward the singularity ahead, and the range of visible wavelengths from outside shifts toward the blue because the object is moving toward the incoming light. The difference between these perspectives, one seeing the object slow to a halt, the other feeling nothing unusual at the crossing, is one of the most profound features of relativity. It reflects the fact that space and time are not absolute. The horizon is not an object in space so much as a feature of spacetime itself, and what it means to cross it depends on where you are and how you move. For rotating black holes, the horizon is accompanied by another boundary outside it, called the static limit. Between the static limit and the horizon lies the ergosphere, a region where space-time is dragged around so strongly by the black hole's spin that no object can remain at rest relative to distant observers. Inside the ergosphere, you can still escape if you move in the right direction, but you cannot stand still. In this zone, even light is carried along by the rotation, its path curved by the frame-dragging effect. The event horizon itself is not fixed in size forever. If the black hole gains mass, by swallowing stars, gas, or even merging with another black hole, the horizon expands. This growth is not a gradual swelling from the inside. Instead, the surface itself changes position in space-time. The reverse is theoretically possible if the black hole loses mass through Hawking radiation. But for astrophysical black holes, this process is so slow that it is irrelevant on timescales much shorter than the age of the universe. One of the remarkable properties of the horizon is its connection to thermodynamics. In the early 1970s, Jacob Bekenstein proposed that a black hole should have an entropy proportional to the area of its horizon. This was a radical idea, because it implied that the horizon somehow encoded information about everything that had fallen into the black hole. Stephen Hawking extended this concept by showing that black holes could emit radiation, gradually losing mass over time. In this picture, the horizon behaves like a hot surface, even though it is not a physical object. Its temperature depends on the black hole's mass, and for large black holes, that temperature is so low it would be swamped by the faint background glow of the universe. The connection between the horizon's area and entropy also led to the area theorem, which states that the total surface area of all event horizons in the universe can never decrease, at least under classical general relativity. When two black holes merge, the area of the resulting horizon is always greater than the sum of the two original areas. This mirrors the second law of thermodynamics, where entropy in a closed system never decreases. In this way, the horizon is not just a marker of here and gone, but a participant in the deep laws that govern the flow of time and the fate of information. Even with all this theoretical understanding, the horizon remains intangible. We cannot touch it, see it directly, or send a probe to hover just above it without it falling in. What we can do is observe its effects on light, on matter, and on space-time itself. The image of the shadow of the black hole in M87, produced by the Event Horizon Telescope, is not the horizon itself, but the silhouette of the photon sphere just outside it. The boundary is invisible, but its influence shapes what we can see. In some speculative theories, the event horizon might not be the absolute barrier it appears to be. Ideas such as firewalls, hypothetical regions of intense energy at the horizon, have been proposed to address the black hole information paradox. Others have suggested that quantum effects could allow information to escape in subtle ways, altering our picture of the horizon's role. So far, these remain theoretical possibilities without observational confirmation, but they highlight the fact that the event horizon is still an active frontier in physics. In the end, the silent boundary is not only a physical limit in the universe, it is also a conceptual one for us. It marks the edge of what we can know about what happens inside, at least for now. Every observation we make about black holes comes from the region outside this boundary, from the behavior of matter and light as they approach it but never cross from our point of view. The interior remains hidden, not because of a lack of technology, but because the structure of the universe itself forbids us from looking in. And just beyond that invisible surface lies the region where time and space swap roles, where every path forward leads to the singularity, and where the familiar rules of cause and effect may be replaced by something we do not yet understand. To approach that place, even in thought, is to move from the known to the unknown, from here to gone, in the most literal sense the laws of physics can allow. Time near a black hole is not what we are used to. This isn't because clocks there suddenly start working differently, or because time itself becomes faulty, but because the geometry of space-time changes the relationship between different observers. Near the event horizon, that relationship is stretched to its limit. For someone far from the black hole, time appears to slow dramatically for anything approaching the horizon. For someone falling in, time continues normally, while the rest of the universe appears to rush forward at an accelerating pace. This difference comes directly from the equations of general relativity. In flat space-time, far from any massive object, we can agree on what a second means. But gravity curves space-time, and in doing so, it alters the paths that both light and matter take. The closer you are to a massive body, the slower your clock runs relative to someone farther away. This is called gravitational time dilation. We experience a tiny version of it here on Earth. Satellites in orbit, slightly farther from the planet's centre, tick a fraction of a microsecond faster each day than clocks on the ground. For GPS systems to work accurately, engineers have to account for this effect. Near a black hole, the difference becomes so extreme that it defines much of what we observe. If you were falling toward the horizon, your own clock would behave normally. Each second for you would feel like a second. But an observer at a safe distance would see your clock slow as you got closer to the horizon, ticking more and more slowly until, at the moment you reached it, it would appear to stop altogether. The light you emitted would also arrive at increasingly longer intervals, redshifted to lower and lower energies until it faded beyond detection. This is not just an optical illusion, it's a real difference in the passage of time between the two frames of reference. From your point of view, you would pass the horizon in finite time and continue toward the singularity. From the distant observer's perspective, you would never be seen crossing it. Instead, your image would grow dimmer and redder, lingering just outside the boundary for eternity. What makes this even more fascinating is how the view works in the opposite direction. As you approach the horizon, the outside universe appears to change. Light from distant stars and galaxies reaches you along increasingly curved paths, and because you are falling inward, much of that light is blue-shifted. It increases in energy. At the same time, the rate at which events appear to happen in the outside universe accelerates. A clock far away might seem to tick faster and faster, and large-scale changes like the movement of stars or even the evolution of galaxies could be compressed into a short period from your perspective. In theory, if you could survive long enough in your fall toward the singularity, you might witness an accelerated version of the universe's distant future. You might see stars burn out, galaxies drift apart, and perhaps even the effects of cosmic expansion over immense timescales. Of course, in practice, the tidal forces and extreme conditions near the singularity make this impossible for any human observer, but the idea emerges naturally from the equations. The way time behaves near the horizon also means that the sequence of events can look different depending on the observer. This is one of the conceptual challenges of black holes. The word when loses its universal meaning. An event that, in your frame, happens after you cross the horizon might be considered to never happen at all by the distant observer, simply because they cannot receive light or signals from it. This breakdown in a shared timeline is not a flaw in the theory, but a feature of relativity itself. This stretching of time is connected to the geometry of space near the black hole. In the Schwarzschild solution, the coordinate that describes time for a distant observer becomes more and more distorted as you approach the horizon. Inside the horizon, the roles of the time and radial coordinates effectively switch. The radial coordinate becomes the one that inevitably decreases, like time does in the outside universe. This means that moving toward the singularity is as unavoidable for you inside as moving toward the future is outside. You cannot choose to stop moving toward it any more than you can choose to stop moving forward in time. In rotating black holes, described by the Kerr solution, the situation is even more complex. Frame dragging twists space-time so that the direction of time itself is not the same everywhere. The horizon still marks the limit beyond which escape is impossible, but the way time flows for different observers depends not only on their distance from the black hole, but also on their motion relative to its rotation. The ergosphere, the region just outside the horizon, is a place where the concept of standing still relative to the distant universe simply doesn't exist. These time effects are not confined to thought experiments. They have practical observational consequences. For example, the matter in an accretion disk orbits close to the event horizon at a significant fraction of the speed of light. The light it emits is both Doppler shifted due to its motion and gravitationally redshifted due to its proximity to the black hole. By studying these shifts, astronomers can infer the location of the inner edge of the accretion disk, which in turn tells them about the black hole's spin and the shape of spacetime around it. The slowing of time near the horizon also plays a role in how black holes evaporate through Hawking radiation. From the perspective of a distant observer, this evaporation is a slow, gradual process, taking far longer than the current age of the universe for any stellar mass black hole. But from the viewpoint of an observer falling into a black hole late in its life, the evaporation might appear to happen much more quickly, compressed into the final moments before reaching the singularity. The interplay between time dilation and observation also feeds into the black hole information paradox. If information about the state of matter that falls in is somehow encoded in the Hawking radiation that escapes, then the timing and nature of that radiation become crucial. But the strange behavior of time near the horizon complicates any attempt to track how such information might escape without violating the principles of quantum mechanics. For all its complexity, the core idea is simple. Time near a black hole is not the same for everyone. The closer you are to the horizon, the more your experience of time diverges from that of the rest of the universe. This divergence is not just an interesting footnote, it is fundamental to how black holes work, to how they appear to us, and to the limits of what we can know about them. And once you understand how time stretches and twists near the horizon, it becomes easier to see why what lies beyond is so inaccessible. The singularity at the centre is not merely hidden by distance or darkness, it is hidden behind a barrier in time itself, one that locks events inside in such a way that they are forever removed from the timelines of those outside. The path inward is also a path forward in time, one that ends in a place where our current laws of physics offer no guidance. From a great distance, the behaviour of anything falling toward a black hole is not what intuition would suggest. Our instincts, shaped by everyday experiences with gravity, tell us that an object will simply accelerate as it approaches the source of gravity, disappearing quickly from view once it gets close enough. That expectation works well for things falling toward planets or stars, where the pull is strong but not overwhelming, and where the escape velocity is always less than the speed of light. But near a black hole, this picture begins to break down. What we actually see from far away is that the falling object appears to slow down as it approaches the event horizon. This isn't because the object itself slows in its own frame, it continues its descent without pause, but because the light it emits takes longer and longer to reach us. Every photon leaving its surface has to fight harder against the gravitational pull of the black hole. The deeper into that pull it is emitted, the more energy it loses on the way out, and the longer it takes to arrive. This energy loss stretches the wavelength of the light, shifting it toward the red end of the spectrum. The process is called gravitational redshift, and it becomes infinite at the horizon itself. From our perspective, this redshift makes the object grow dimmer and redder over time. If we could somehow detect every wavelength, no matter how long, we might still see it, but in reality our instruments and our eyes have limits. As the light stretches beyond those limits, the object simply fades away, long before it would actually cross the horizon in our view. In practical terms, anything that falls in seems to freeze just above the event horizon, its image slowly dissolving into the blackness. There is also the matter of timing. Each successive signal from the falling object is delayed relative to the previous one, because the space-time between it and us is increasingly distorted. From far away, the intervals between those signals grow without bound, so that the final moments of the object's fall appear to be stretched over an infinite period of our time. This is why, in the distant observer's frame, the object never appears to actually cross the horizon. It just gets closer and closer, forever. This is a deeply counterintuitive result, but it emerges naturally from the geometry of general relativity. It doesn't matter how powerful your telescope is, or how patient you are. The light carrying information from the moment of crossing can never reach you. It is trapped by the same structure of space-time that traps the object itself. If we could see this process in extreme detail, we would notice other effects as well. The gravitational field near the black hole not only redshifts the light but also bends it, altering the apparent shape of the object. If the object is small enough and close enough, light from its far side can be bent around the black hole and reach us, so we might see multiple distorted images of it at once. In some cases, the light can orbit the black hole one or more times before escaping, producing strange lensing effects that no everyday experience could prepare us for. The view is different if we imagine ourselves falling with the object. From that perspective, there is no slowing down, no infinite delay, no fading away. The crossing of the horizon happens in finite time, and there is nothing special to mark it. No sudden darkness, no barrier, no sensation of passing a point of no return. The only hints come from the behaviour of the outside universe. As we fall, the light from outside grows brighter and more concentrated toward one direction, blue shifted by our motion and by the gravitational well we are descending into. The rest of the universe appears to speed up, as if time outside is being compressed into the moments before we reach the singularity. The difference between these two views, ours from far away and that of the falling object, is not a contradiction. It is a consequence of relativity, which tells us that space and time are not fixed, universal quantities, but depend on the observer's position and motion. Each frame of reference is internally consistent, and each tells a different but equally valid story about the same event. The seeming paradox arises only if we try to combine the two, without accounting for the curvature of space-time. This split in perspectives also has implications for how we think about the fate of information and matter that falls into a black hole. From the distant observer's standpoint, the object never actually disappears, it just becomes undetectable as its light is redshifted away. In some interpretations, this suggests that the information it carries remains encoded in the gravitational and quantum fields just outside the horizon, perhaps to be released later through Hawking radiation. From the falling object's point of view, however, it passes into the interior without hesitation, carrying its information with it toward the singularity. Reconciling these two pictures is at the heart of the black hole information paradox. There is also a practical aspect to this difference in views. When astronomers talk about matter falling into a black hole, what they actually observe is matter approaching the horizon, heating up, and radiating energy before it fades from view. This is why we can see accretion disks glowing brightly, even though the event horizon itself emits nothing. The disk's inner edge can be incredibly close to the horizon, and the radiation from that region is often in the X-ray part of the spectrum, created as gas is compressed and heated by the immense gravitational forces. Sometimes matter falling toward a black hole doesn't just fade quietly. Interactions in the accretion disk can launch jets of material along the black hole's spin axis, travelling at nearly the speed of light. These jets are powered by magnetic fields and the rotational energy of the black hole, and they can extend for thousands of light years. From our perspective, they can outshine the galaxy that hosts the black hole, yet the material in them never comes from inside the horizon. It is launched before crossing that invisible boundary. In all of this, the essential point remains. What we see from the outside is not what happens for the infalling object. Our view is shaped by the way light and time behave near the horizon, and it is incomplete by design. The event horizon is not just a physical barrier, it is a barrier to communication, a line beyond which information cannot travel back to us. That's why the region beyond it remains hidden, no matter how close we look. And yet, the interplay between these perspectives is what gives us so much of our understanding of black holes. By studying how matter behaves as it approaches the horizon, how its light shifts and fades, how its timing changes relative to the outside universe, we can infer properties of the black hole itself. We can measure its mass, estimate its spin, and test the predictions of general relativity in some of the most extreme conditions possible. The fact that we can never see the actual crossing is not a limitation of our instruments. It is a fundamental feature of the universe, and once that crossing happens in the falling object's own frame, there is no coming back, not in space and not in time. Imagine deciding, for reasons of science, curiosity, or perhaps an acceptance of finality, to take a deliberate course toward a black hole. The journey begins far from it, where space looks much like anywhere else in the universe. The black hole itself is not visible. What you can see from here is the space around it, light from distant stars subtly distorted, the occasional faint glimmer from gas or dust drawn in and heated on its way down. The darkness at its centre is not a solid shape, but an absence, a place where no light escapes to your eyes. Approaching slowly at first, there is little to suggest anything unusual. The gravitational pull from far away is no different in kind from that of a star or planet, just stronger for the same mass because of the compactness. You could orbit at a safe distance indefinitely, feeling nothing out of the ordinary. As you close in, the pull strengthens, and the first noticeable change comes not from acceleration but from the view. Stars behind the black hole begin to stretch into arcs as their light is bent around it, and those arcs grow longer and brighter as you draw closer. If you pass through a region where gas is being drawn in, a thin accretion disk, your surroundings may light up dramatically. The disk would be brightest close to the black hole, glowing in X-rays and extreme ultraviolet. In visible light, it might be blindingly white near the centre, fading to yellow and orange as you move outward. You might see turbulence, bright spots where clumps of matter collide and heat, and perhaps flickering patterns from magnetic fields twisting the charged particles. All of this activity would be outside the horizon, in a place where radiation can still escape. As you line up for a direct plunge, the sense of acceleration becomes overwhelming. In empty interstellar space, acceleration is not something you feel unless it's resisted by a force. In free fall, you're weightless, but the changing scenery gives the reality away. The black region ahead grows larger, its edge ringed by a warped and distorted panorama of the universe. This ring is the photon sphere, where light can orbit the black hole in unstable paths. From here, photons can make partial or complete loops before escaping, so you might see multiple images of the same star in different places around the ring. Crossing into the photon sphere, the distortions become so extreme that most of what you see is no longer recognizable as individual objects. The light from behind is bent into a shrinking halo around the black center. Every direction you look, save for directly ahead, now contains some version of the outside universe, smeared and twisted by gravity. If your destination is a stellar mass black hole, the experience from here becomes short and violent. The tidal forces increase rapidly as you approach the horizon. If you're falling feet first, the difference in gravitational pull between your feet and your head becomes more than your body can withstand. Even in a pressurized, reinforced craft, the structure would be stretched along the axis of motion and compressed along the perpendicular directions. Your body would be elongated, your tissues and eventually your atoms pulled apart in the process we call spaghettification. For a supermassive black hole, this stretching is negligible at the horizon, so you could cross it intact, unaware that you had passed a point from which escape was impossible. The crossing itself offers no physical sign. Your instruments, however, might detect the change. Outgoing signals, radio, light pulses, any attempt to communicate would fail to reach outside observers from this moment on. From your own perspective, they would be sent normally, but they would never arrive. To you, the interior is just the next stage of the journey. To the outside, you're gone. Inside, the rules of space and time shift. The radial direction toward the singularity becomes as inevitable as the forward march of time in the outside universe. No amount of thrust or maneuvering could take you back toward the horizon. It is now as unreachable as yesterday is to us. The singularity lies ahead in the same way the future does, unavoidable, fixed in your personal timeline. The view behind you compresses into a small bright disk of the outside universe. All the light from the cosmos pours in from that shrinking patch, increasingly blue-shifted as you move inward. If you're close to the horizon of a rotating black hole, the image might twist and whirl, shaped by the black hole's spin. Frame dragging pulls space itself into rotation, and you feel this as a tendency to move along with it, even without firing a thruster. For a while, minutes or even hours depending on the mass, you could continue without immediate harm inside a supermassive black hole. But the tidal forces grow as you descend. Eventually they surpass the strength of your body, your ship, even the atomic bonds in matter. Before you reach the singularity, you're stretched into an ever thinner filament, your structure and information scattered in a way we do not yet fully understand. Whether that information is truly destroyed or somehow preserved in the fabric of space-time is one of the most challenging open questions in physics. In the rotating case, the singularity itself is not a point but a ring, with a central region that some mathematical solutions suggest could connect to other regions of space-time. This is highly speculative and almost certainly unstable, but the mathematics leaves room for strange possibilities that no one has yet been able to confirm or rule out. Regardless, the fate of anything crossing the horizon is sealed. It cannot return to the universe it left. From the outside, none of this is visible. The moment you pass the horizon, you are lost to any signal, and the last images anyone could have seen were already fading and redshifting toward invisibility. To them, you still hang just above the horizon, frozen in time, while in your own frame, you are long past that point and falling toward the inevitable. A hypothetical journey like this is not one we could ever reverse, even in theory. The event horizon is not a wall you can bounce off. It is a one-way gate in the structure of space-time. Crossing it is not simply a matter of going somewhere else. It is a change in your relationship to time and space themselves. Everything inside is part of a future that cannot connect back to the past outside. And this is where the story of such a journey inevitably becomes one about limits. Not the limits of our technology, but the limits set by the universe itself. The black hole is not merely a place where light is trapped. It is a place where causality, as we understand it, is bounded. The traveller's path ends in a region where the equations break down, where the known laws no longer tell us what happens. And yet, the approach to that place is governed by rules we can calculate precisely, rules that have been tested again and again in the motions of stars, the bending of light, and the stretching of time. The traveller in this thought experiment becomes both a participant in and a casualty of those rules. The outside observer watches them fade, the inside observer feels the pull, and both are correct in their own frames. Between these two truths lies the real boundary, a horizon not just in space, but in knowledge. When Stephen Hawking first described what would come to be known as Hawking radiation in the mid-1970s, it was an unexpected twist in the story of black holes. Up to that point, the general assumption was that nothing could escape from within the event horizon. This was part of what made black holes seem so absolute. Once matter or light crossed that boundary, it was gone forever. The idea that black holes could in any sense emit anything at all was considered contradictory to their very definition. Yet Hawking's calculations showed otherwise, and in doing so, they reshaped how we think about the life cycle of these objects. The starting point was the recognition that the vacuum of space is not truly empty. Quantum field theory tells us that, even in regions devoid of matter and light, fields still fluctuate. These fluctuations can briefly produce pairs of particles and antiparticles, which appear together, borrow a tiny bit of energy from the vacuum, and then annihilate one another, returning the energy and restoring the vacuum's balance. Under normal circumstances, this happens everywhere in space, without any lasting effect, the particles disappearing almost as soon as they appear. Near the event horizon of a black hole, however, the situation becomes more interesting. If such a particle-antiparticle pair forms right at the edge, it is possible for one to fall into the black hole while the other escapes to infinity. To an outside observer, it looks as though the black hole has emitted a particle. Energy conservation requires that the black hole lose an equivalent amount of mass in the process, so over time, this emission causes the black hole to shrink. The result is a slow leakage of energy in the form of radiation from something that was once thought to be utterly sealed. Hawking radiation is incredibly weak for large black holes. For a stellar mass black hole, one a few times the mass of our Sun, the radiation is negligible compared to the faint microwave glow of the universe's cosmic background. The temperature associated with this radiation, as calculated by Hawking, is inversely proportional to the black hole's mass. The bigger the black hole, the colder it is, and the less radiation it emits. A supermassive black hole, millions or billions of times the Sun's mass, would have a temperature so low that it would be effectively undetectable by any current technology. This means that for most black holes we know of, Hawking radiation plays no role in their day-to-day existence. They gain mass from the matter they capture far faster than they lose it through this process. But in the deep future, when stars have burned out and galaxies have gone dark, Hawking radiation will become the dominant mechanism by which black holes change. Without new material to consume, they will slowly lose mass, their horizons shrinking, their temperatures rising as they get smaller. This last detail is counterintuitive. Unlike ordinary objects, black holes get hotter as they lose mass. As the mass decreases, the radiation becomes more intense, and the rate of evaporation accelerates. A black hole that has existed quietly for trillions of years will, in its final moments, release a burst of energy far greater than anything it emitted before. For stellar mass black holes, these final moments would be brief but spectacular, producing a flash of high-energy particles and radiation. For smaller black holes, if such primordial ones formed in the early universe and still exist, the process could be happening now, though none has yet been detected. The existence of Hawking radiation also has profound implications for the laws of physics. If black holes evaporate entirely, what happens to the information about the matter that formed them or fell into them over their lifetimes? In classical physics, that information would be lost forever inside the singularity, inaccessible to the outside world. But in quantum mechanics, information is never truly destroyed. The evaporation process raises the question of whether the radiation somehow carries that information away, or whether it is lost in a way that violates one of the core principles of quantum theory. This conflict between general relativity and quantum mechanics is known as the black hole information paradox, and it remains unresolved. Some physicists have suggested that the information might be encoded in subtle correlations between the particles in Hawking radiation, making it possible, in principle, to reconstruct the original state of the matter that formed the black hole. Others propose that the information might be preserved in a remnant left behind after evaporation, or that the event horizon itself is not quite what classical general relativity predicts, but instead some kind of quantum surface capable of storing and releasing information. These ideas are still speculative, and none has yet been confirmed by observation or experiment. Despite its weakness for large black holes, Hawking radiation has become a critical concept in theoretical physics. It bridges the gap between quantum field theory and general relativity, applying quantum principles to curved spacetime and showing that even the most extreme gravitational objects obey the rules of thermodynamics. The fact that a black hole has a temperature, and therefore an entropy, links it to the same statistical principles that govern heat, energy flow, and disorder in every other system in the universe. This connection has inspired new ways of thinking about spacetime itself. Some approaches to quantum gravity, attempts to unite general relativity with quantum mechanics, suggest that the entropy of a black hole, proportional to the area of its horizon, tells us something fundamental about the nature of spacetime at the smallest scales. In these views, the horizon's area is a measure of the number of quantum states available inside, and the fact that this measure is finite may hint at a discrete, granular structure to space-time. In the more immediate sense, Hawking radiation also changes how we view the ultimate fate of black holes. Without it, a black hole could, in principle, persist forever, growing if it found new sources of mass but otherwise remaining unchanged. With it, every black hole has a finite lifetime, however long. Even the most massive ones will eventually vanish, returning their mass to the universe in the form of radiation. In a cosmos without new sources of energy, the evaporation of black holes could be the last major event before everything settles into a cold, dark equilibrium. It is worth noting that Hawking's original derivation relied on treating the black hole as a fixed background, with quantum fields living in that space-time. Later refinements and extensions have examined what happens when the black hole's changing mass is taken into account, and how the radiation interacts with other aspects of the environment. None of these refinements has overturned the basic conclusion: black holes radiate, and in doing so, they eventually evaporate. The prospect of detecting Hawking radiation directly from astrophysical black holes is remote, given the incredibly low temperatures involved. Some experiments have instead sought analog systems in the laboratory, where certain fluid flows or optical systems can mimic the behavior of an event horizon for waves. In these analog gravity setups, researchers have observed effects that parallel Hawking's predictions, lending indirect support to the idea, even if the actual astrophysical phenomenon remains beyond our reach for now. For all its theoretical importance, Hawking radiation has a kind of quietness to it. It does not roar like the jets from an active galactic nucleus, or flash like a supernova. It is a slow, steady whisper of energy from an object that otherwise absorbs everything around it. It takes the stillness of the black hole and gives it the faintest of voices, one that will only truly be heard when the rest of the universe has gone silent. The fact that this whisper can carry away the very mass of the black hole, and perhaps the information it contains, means that it is more than just a curiosity. It is a reminder that even the most seemingly permanent features of the cosmos are subject to change, and that the boundaries we once thought absolute may, under the rules of quantum physics, have subtle ways of allowing the outside world a glimpse, however small, of what lies within. At the centre of every black hole, according to classical general relativity, lies a singularity, a place where the known laws of physics no longer apply. In the equations, it appears as a point of infinite density, where all the mass of the black hole is compressed into zero volume. Spacetime itself is said to curve infinitely here, and concepts like length, duration, and even direction lose their meaning. On paper, the singularity is unavoidable, the natural consequence of gravity unchecked, drawing matter inward until there is no inward left to go. But in reality, this infinite point is a sign that something about our understanding is incomplete. In the earliest days of black hole theory, before the term was even coined, the idea of such a singularity was troubling to physicists. It was not that they doubted the mathematics, rather, they knew that infinities in a physical theory are usually warnings. An infinity in a calculation often means that the model being used has reached beyond its domain of validity. Newton's laws break down at very small scales, and so do the familiar rules of quantum mechanics when applied without modification to the intense gravity of a black hole centre. The singularity in this sense is not necessarily a real object or place, but a marker that our current theories have run out of predictive power. Still, Within general relativity, the singularity is unavoidable. The singularity theorems proved by Stephen Hawking and Roger Penrose in the 1960s showed that if certain reasonable conditions hold, such as the existence of matter with positive energy density, then a gravitational collapse that passes the event horizon will lead to a singularity in finite proper time for the infalling matter. This means that, inside the horizon, the collapse cannot stop partway. It must continue until all paths in spacetime end in this point of infinite curvature. In the simplest, non-rotating black holes described by the Schwarzschild solution, the singularity is a single point in space, but for the infalling matter, it is a moment in the future, as inevitable as tomorrow is for us. In rotating black holes, described by the Kerr solution, the singularity is not a point but a ring. The mathematics here is even stranger. There are solutions in which passing through the ring, singularity could, in principle, take you to another region of space-time, perhaps even another universe. These possibilities arise from the equations themselves, but they are widely believed to be unrealistic for actual astrophysical black holes, as they do not account for the likely instability of such a passage under even the smallest disturbances. From a physical standpoint, the singularity's defining feature is that it is hidden behind the event horizon. This means that, in principle, whatever happens there cannot influence the outside universe directly. The cosmic censorship conjecture, proposed by Penrose, suggests that this is always the case, that nature censors singularities by keeping them hidden behind horizons. This protects the rest of space-time from the breakdown of predictability that the singularity represents. Without this cosmic boundary, the behavior of the universe could become chaotic, as events near a naked singularity could affect the rest of the cosmos in ways no current theory can describe. One reason the singularity is so hard to picture is that the space and time coordinates we use outside the black hole swap roles once inside the horizon. Outside, you can choose whether to move closer or farther from the black hole, but you cannot choose to stop moving forward in time. Inside, the radial coordinate, distance to the singularity, becomes like time. It must always decrease. No matter what you do, you are carried inevitably toward the center. In this sense, the singularity is not so much a location in space, as it is a moment in your future that you cannot avoid. The nature of the singularity is one of the strongest motivations for seeking a theory of quantum gravity. General relativity works beautifully for large-scale structures and moderate gravitational fields, but at extremely small scales, on the order of the Planck length, it cannot be complete. Quantum mechanics must play a role there, and whatever theory unites the two should, in principle, tell us what happens where general relativity currently predicts an infinite curvature. Some proposals suggest that the singularity might be replaced by a region of extremely dense but finite matter, or that spacetime itself might be quantized, with the smallest possible units preventing true infinite compression. Loop quantum gravity, for example, replaces the continuum of spacetime with a discrete structure, like a network of finite loops. In this framework, the collapse toward a singularity could be halted by quantum effects, creating a kind of bounce that either stabilizes the core or leads to the creation of a new expanding region, what some call a white hole. String theory, another major approach, replaces point-like particles with one-dimensional strings whose vibrations give rise to the properties of matter. In some versions of string theory, the singularity might be smoothed out into a finite structure or replaced by a complex topology that avoids infinite curvature altogether. Observationally, we cannot see the singularity itself, but we can study the regions just outside the horizon to test whether our current understanding holds. Precise measurements of the orbits of stars near Sagittarius A, the supermassive black hole at the center of the Milky Way, and detailed imaging of the shadow of M87's black hole give us indirect tests of general relativity under extreme conditions. So far, the results agree remarkably well with the predictions, but they do not yet tell us what happens deep inside, where the singularity would be. In the long term, Hawking radiation means that a black hole will shrink and eventually vanish. What happens to the singularity when the horizon disappears is an open question. If the black hole evaporates completely, the singularity must either vanish with it or transform into something else. If quantum mechanics is right that information cannot be destroyed, then the structure at the core of the black hole must somehow release its information or have already encoded it in the radiation that escaped over its lifetime. This is where the singularity becomes more than a mathematical curiosity. It becomes central to some of the deepest unsolved problems in physics. It is both the end point of matter's journey into a black hole and the point at which our theories meet their limits. It may hold the key to understanding the unification of forces, the nature of space-time, and perhaps even the origin of the universe itself, since the Big Bang can be described as a kind of singularity in reverse. What is certain is that the singularity, whatever it is, cannot be reached without crossing the event horizon, and once crossed, the journey toward it is inevitable. It is the final destination for everything that falls in, the ultimate one-way trip. And until we have a complete theory that unites the large-scale geometry of relativity with the small-scale granularity of quantum mechanics, it will remain a place of mystery. Not just because we cannot see it, but because we cannot yet imagine it without breaking the rules that guide all our other imaginings. One of the most common misconceptions about black holes is that the event horizon is some kind of solid boundary, a literal surface floating in space, like the skin of a sphere, which you might bump into if you approached it. This is understandable, because our everyday experiences with boundaries involve something physical: walls, floors, planetary surfaces. But the event horizon is not a surface in any material sense. It is not made of matter, nor is it a layer of energy or particles. It is not even a place in the traditional way we think of locations. It is a feature of space-time geometry, a boundary defined entirely by the paths that light and matter can take. The simplest way to describe it is to say that the event horizon is the dividing line between where escape is possible and where it is not. In that sense, it is more like the edge of a waterfall than the edge of a cliff. If you're in a boat upstream from a waterfall, there's a point where the current becomes too fast to row against. If you pass that point, you will be carried over no matter what you do, not because there is a wall there, but because the flow of the river has become irresistible. In the case of a black hole, the flow is the curvature of space-time itself, and the speed limit you can row against is the speed of light. From a distance, nothing marks the horizon except its effect on light. A beam aimed outward just from inside will never reach the outside universe, while one aimed outward from just outside can. The closer you are to it, the more difficult escape becomes, until at the horizon it becomes impossible. There is no physical layer to cross. Rather, the horizon is a location in the space-time map where the escape velocity reaches the speed of light. Because it is not a material surface, you would feel nothing unusual when crossing it. Assuming the black hole is large enough that tidal forces at the horizon are small, your spacecraft would not jolt or shake. No alarms would sound simply because you reached this location. In your own frame of reference, the crossing would be uneventful, yet from the point of view of an observer far away, your approach to the horizon would appear to slow, and your signals would stretch out in time and fade away. This is one of the most fascinating aspects of the event horizon. It has no physical thickness or texture, but it still separates two fundamentally different regions of the universe. Mathematically, the horizon is defined by what's called a null surface, a surface traced out in space-time by light rays that are just on the edge of escaping. These light rays hover there forever in the coordinates of a distant observer, neither falling inward nor escaping outward. Anything inside this surface is inevitably carried toward the singularity. The horizon's position depends on the black hole's mass, charge, and spin, and it can change if the black hole gains or loses mass. When matter falls in, the horizon grows. When the black hole emits Hawking radiation, it shrinks. The fact that the event horizon is not a physical surface is one reason why the idea of black holes as objects can be misleading. A black hole is not a solid thing surrounded by a shell. It is a region of space-time with certain properties, and the horizon is simply the outermost limit of that region. Inside, space-time is curved in such a way that all possible paths lead toward the singularity. Outside, there are paths that lead away to infinity. The horizon is where those possibilities change from one to the other. In rotating black holes, the concept becomes even more nuanced. The event horizon is still the boundary beyond which nothing can escape, but it is accompanied by another boundary farther out called the static limit. Between the static limit and the horizon is the ergosphere, where space-time is dragged around by the black hole's rotation. Inside the ergosphere, you can still escape if you move in the right direction, but you cannot remain stationary with respect to distant stars. This makes the horizon even less like a surface and more like a geometric feature, something that exists because of the way space-time is being twisted, not because of any physical material. Because the horizon is not a surface, it does not have a temperature or colour in the ordinary sense. When we talk about the temperature of a black hole due to Hawking radiation, we mean a property of the horizon in the context of quantum field theory in curved space-time. This temperature is not from any physical surface radiating like a star's photosphere, but from the way the quantum vacuum behaves near the horizon. Similarly, when we speak of the area of the horizon, we mean the area of this null surface as calculated from the geometry, not an actual physical membrane. That said, there are intriguing ideas in theoretical physics where the horizon could behave as if it were a kind of surface in some descriptions. The membrane paradigm treats the horizon as if it were a thin conducting shell with certain properties, like viscosity and electrical resistance. This is not a literal description. It's a mathematical tool that allows physicists to model the interactions between black holes and electromagnetic fields in a way that is easier to visualize. In this picture, an outside observer can think of the black hole as having a surface just outside the horizon, even though this surface is entirely a construct and does not exist for someone falling in. This distinction between how the horizon appears to an outside observer and to an infalling one is central to many modern debates in black hole physics. The firewall hypothesis, for example, suggests that quantum effects could produce a region of intense energy right at the horizon, effectively turning it into a physical barrier that would destroy anything falling in. This idea was proposed as a possible solution to the information paradox, but it conflicts with the predictions of general relativity, which say that the crossing should be smooth. Whether such a firewall exists is still unknown, and it remains one of the more controversial ideas in the field. In everyday terms, the horizon is more like a point of no return in a story than a locked door or a wall. You can pass it without noticing, but once you do, the narrative is set. You are on a path that cannot be reversed. It is a conceptual boundary rather than a tangible one, defined by what is possible and what is impossible according to the geometry of space-time. And like many conceptual boundaries in physics, it is invisible yet absolute, intangible yet inescapable. Because it is so unlike any boundary we experience in daily life, the event horizon challenges our intuitions. We are used to thinking of limits as things we can see or touch, things that physically block our way. The horizon does not block, it simply reshapes the possibilities for movement in such a way that escape ceases to be one of them. Its existence is a mathematical consequence of Einstein's equations, and its effects are measurable, but it is not an object in space. It is part of the fabric of space-time itself. For all its abstraction, the event horizon is what gives a black hole its defining quality. Without it, we would simply have an extremely dense object, perhaps with a visible surface, like a neutron star. With it, we have a region from which no light or matter can return, a perfect absorber in theory, and a test bed for the interplay between gravity, quantum mechanics, and thermodynamics. And yet, despite its central role, it is nothing you could touch, nothing you could stand on, nothing that exists in the same way as the ship you arrive in, or the stars you see in the sky. It is a reminder that in the universe, not all boundaries are made of matter, and not all limits are marked by edges you can feel. Some exist only in the map of possibilities, drawn not by hand, but by the fundamental laws of nature themselves. The event horizon is one of these, a pure geometry that divides what can be from what cannot, and does so without ever taking on the substance of a surface. At the centre of most large galaxies, including our own Milky Way, there is a massive gravitational anchor, a black hole whose mass is millions or even billions of times that of the Sun. These supermassive black holes are among the largest single concentrations of mass in the known universe, yet their presence is felt far beyond their immediate surroundings. They are not just passive consumers of matter, they play an active role in shaping their host galaxies, influencing the distribution of stars, the motion of gas, and even the pace of star formation over cosmic time. Our own galaxy's central black hole, Sagittarius A, has a mass of about 4 million suns. By black hole standards, this is on the smaller end for a supermassive one. Its event horizon has a diameter roughly 25 million kilometers, about 17% of the distance from Earth to the Sun. But this vast scale is tiny compared to the galaxy around it. Despite its enormous mass, Sagittarius A is quiet now, with only a trickle of material falling in. Yet we know from observations of other galaxies that supermassive black holes can be anything but quiet when they are actively consuming matter. The discovery that such massive objects lie at the cores of galaxies came gradually. In the 1960s, astronomers studying distant quasars noticed that they were incredibly luminous, outshining entire galaxies despite being no larger than our solar system. The only plausible explanation for this energy output was the gravitational potential energy released as matter fell into a supermassive black hole. Over time, improved observations revealed that the centers of many, perhaps most galaxies contain similar objects, sometimes active, sometimes dormant, but always there. In nearby galaxies, the motions of stars and gas can be measured with enough precision to reveal the gravitational influence of something very dense at the center. The orbits of stars near Sagittarius A have been tracked for decades, with one star, S2, completing a full orbit in just 16 years. The tightness of these orbits, combined with the mass inferred from their speeds, leaves no room for any ordinary object. The mass is too high, and the volume too small for anything other than a black hole. One of the most striking features of supermassive black holes is the correlation between their mass and the properties of their host galaxies. In particular, there is a strong relationship between the mass of the black hole and the velocity dispersion of stars in the galaxy's bulge, the region around the center. This suggests that the growth of black holes and the evolution of galaxies are linked, though the details of that connection are still being explored. It may be that energy and momentum from the black hole's activity regulate the amount of gas available for star formation, creating a feedback loop between the two. When a supermassive black hole is actively accreting, the process can be extraordinarily energetic. As gas spirals inward through the accretion disk, it heats to millions of degrees, emitting light across the electromagnetic spectrum. In some cases, powerful jets of plasma are launched from near the poles of the black hole, travelling at close to the speed of light. These jets can extend for hundreds of thousands of light years, carrying energy far into intergalactic space. They are powered not just by the infalling matter, but also by the rotation of the black hole itself, through mechanisms that tap into the twisting of magnetic fields in the curved space-time. These energetic outflows can have dramatic effects on the galaxy. They can heat or expel the gas that would otherwise cool and condense into new stars, slowing or halting star formation for millions of years. At the same time, they can compress gas clouds in some regions, triggering bursts of star formation. The balance between these effects is complex, and different galaxies may experience them differently depending on the timing, strength, and direction of the activity. The formation of supermassive black holes remains one of the outstanding questions in astrophysics. Did they grow from smaller seed black holes left behind by the first generation of stars? Or did some form directly from the collapse of massive gas clouds in the early universe? Observations of very distant quasars, seen as they were less than 1 billion years after the Big Bang, show that supermassive black holes with masses of 1 billion suns already existed by that time. This rapid growth challenges our understanding of how quickly black holes can accumulate mass, leading to theories involving unusually massive seeds or episodes of extremely efficient accretion. In the local universe, many supermassive black holes are relatively inactive, including our own. But even a dormant black hole can be briefly reawakened if a star wanders too close. In such a tidal disruption event, the star is torn apart by gravitational forces and some of its material is flung outward, while the rest falls toward the black hole, creating a temporary flare of radiation. These events provide rare opportunities to study the feeding process in detail, as the light from the flare carries information about the dynamics and geometry of the accretion flow. Supermassive black holes are also sources of gravitational waves when they merge. When two galaxies collide, their central black holes sink toward the merged center, over time, eventually forming a binary. The slow-in spiral of such massive pairs produces gravitational waves at very low frequencies, detectable by pulsar timing arrays that monitor the regular pulses of distant neutron stars. These signals are beginning to reveal a background hum of gravitational waves from many such mergers across the universe. In the future, space-based detectors will be able to observe individual mergers directly, opening another window on the growth and evolution of these giants. The role of supermassive black holes in galaxy evolution is still being pieced together, but it is clear that they are not isolated curiosities. They are integral parts of the systems they inhabit, shaping the flow of matter and energy on scales far larger than their own. Their gravity governs the orbits of stars in the central regions. Their radiation can outshine the rest of the galaxy, and their jets can influence the intergalactic medium. Over billions of years, these effects add up, leaving an imprint that can be seen in the structure and history of galaxies across the cosmos. In the end, these black holes are both anchors and engines. They anchor their galaxies through their immense gravity, holding the central stars in tight orbits. They act as engines when active, driving outflows that can reshape the galaxy's future. And though they are hidden from direct view by their own horizons, the marks they leave on their surroundings tell us that they are among the most important players in the grand story of cosmic structure. For most of the time we've known about black holes, they existed only as ideas in our minds and as patterns in the mathematics. We could see their effects on nearby stars and gas, infer their presence from the way light bent or the way matter moved, but no one had ever seen one directly. That was the nature of the puzzle. They are by definition invisible. The event horizon lets nothing escape, so there is no light to capture, no surface to photograph. For decades it seemed inevitable that they would remain forever unseen except through their influence on other things. The shift towards seeing the unseeable began with the realization that you do not have to see the black hole itself to see its outline. Matter falling toward the event horizon releases energy, and in some cases that energy comes in the form of intense light from an accretion disk. If you could capture that light with enough resolution, you might see the way it bends around the black hole before reaching you. In principle, the result would be a silhouette, the black shadow of the event horizon against the glowing background of infalling material. This shadow is larger than the horizon itself, because light passing close to the black hole is pulled inward, creating a boundary for visible photons known as the photon sphere. The challenge was resolution. The shadow of the supermassive black hole at the center of our galaxy, for example, is tiny from our vantage point, about the size of a grapefruit on the surface of the moon. Even the largest individual radio telescopes could not hope to see something that small. To capture such detail, you would need a telescope the size of the Earth. Building such a thing physically is impossible, but there is another way. Link telescopes scattered across the globe so they act together as one. This technique, called very long baseline interferometry, uses multiple radio observatories spread over thousands of kilometers. Each telescope collects signals from the target, and the timing of those signals is recorded with extraordinary precision using atomic clocks. By later combining the data from all participating sites, astronomers can effectively create an Earth-sized virtual telescope with a resolving power far beyond any single dish. The shorter the wavelength of light you use, the finer the detail you can resolve, and for this work, astronomers turn to millimeter wavelength radio light, which can pass through the dust and gas that obscure galactic centers. The idea of using such a network to image a black hole's shadow had been discussed for years, but it wasn't until the formation of the Event Horizon Telescope collaboration that it became a coordinated global effort. This international team linked observatories from Hawaii to Spain, from Chile to the South Pole, covering as much of the Earth's surface as possible. Every additional baseline, the distance between two participating telescopes, adds more detail to the virtual image. The first target was not our own Sagittarius A, but the much larger black hole in the galaxy M87. Located 55 million light-years away, M87's central black hole has a mass about 6.5 billion times that of the Sun, making it enormous even by supermassive standards. Its shadow is far larger than that of Sagittarius A, and although it is farther away, its angular size in our sky is roughly comparable. Importantly, it is also more stable in appearance. Sagittarius A changes on timescales of minutes due to the rapid motion of material close to the horizon, while M87's scale is so vast that changes occur over days or weeks, making it easier to image with the long integration times required. In April 2017, the Event Horizon Telescope Network conducted a week-long observing campaign, collecting petabytes of data. This data could not simply be sent over the internet. Instead, it was physically transported on hard drives to central processing centers, where the signals from each telescope were combined. The correlation process had to account for tiny differences in timing, the rotation of the Earth, atmospheric effects, and countless other variables. The final image would emerge not from a single exposure, but from the careful reconstruction of interference patterns in the radio waves collected around the globe. 2 years later, in April 2019, the result was revealed to the world: a bright ring of emission surrounding a dark central region, the first direct visual evidence of a black hole's shadow. The image of M87 then matched the predictions of general relativity with remarkable accuracy. The size and shape of the ring agreed with theoretical models for a black hole of its mass and spin, and the Earth's symmetry and brightness was consistent with material in the accretion disk moving toward us on one side and away on the other, boosting the light through relativistic beaming. This achievement was not just a technological triumph, but a conceptual one. For the first time, humanity had seen a feature of a black hole itself, not merely the effects on its surroundings. It confirmed that the photon orbits and light-bending behavior predicted by Einstein's equations hold true even in the most extreme environments we can observe. The black hole's shadow is not a hard surface, it is a boundary in the paths of light rays, but it is visible in a way that lets us test our theories. Soon after, the focus turned to Sagittarius A's. Imaging it posed unique challenges, despite being much closer. Its smaller mass means that matter orbits near the horizon in minutes rather than days, causing the appearance of the emission region to change rapidly during an observing session. To deal with this, the Event Horizon Telescope team developed new methods to reconstruct an average image from the fluctuating data, resulting in a view that again showed a ring of light surrounding a dark center. The size of this ring matched the predictions for a black hole of about 4 million solar masses, providing yet another confirmation of general relativity. These images do not show the event horizon itself, nothing can, but they show the shadow it casts on the light around it, which is the closest thing we can observe. In the same way that a ship's wake tells you where it has been and how it moves, the shadow tells us about the horizon's size, the black hole's mass, and the bending of spacetime in its vicinity. The work of imaging black holes is ongoing. More observing stations are being added to the network, increasing resolution and sensitivity. With more baselines and improved techniques, astronomers hope to produce sharper images, detect changes over time, and even create movies showing the dynamics of the accretion flow. Future observations might reveal the structure of jets near their launch points, test the details of the spacetime geometry, and search for subtle deviations from Einstein's predictions that could hint at new physics. Seeing a black hole's shadow for the first time was a milestone in human exploration, not because it took us physically closer, but because it brought the invisible into view. For generations, black holes were things we knew only through mathematics and indirect evidence. Now, we can look at an image and know that the darkness in the centre is not just an absence of light. It is the mouth of a gravitational well so deep that nothing can climb out. It is the very definition of the point of no return, captured in a ring of light bent by the most extreme gravity we can find. When most people think of black holes, they imagine them as voracious consumers, devouring anything that comes too close and giving nothing back. This picture, while true in the most literal sense for the region inside the event horizon, leaves out a remarkable and perhaps counterintuitive reality. Black holes can also be among the most powerful sources of energy in the universe. They are not simply sinks of matter and light. They can act as engines, transforming the gravitational energy of infalling matter into radiation, motion, and even vast coherent structures that stretch across intergalactic space. The key to this lies not inside the event horizon, but in the space just outside it, where matter collects and accelerates before crossing the point of no return. When gas falls toward a black hole, it rarely plunges straight in. Instead, it arrives with some angular momentum, which causes it to orbit and gradually spiral inward. This process forms an accretion disk, a flattened, rotating structure of hot plasma that radiates energy as it loses angular momentum and moves closer to the horizon. The efficiency of this process is astonishing. In a typical nuclear fusion reaction inside a star, less than 1% of the rest mass energy of the fuel is converted into light and heat. In contrast, the accretion of matter onto a black hole can convert 10% or more of the infalling mass's energy into radiation. For a spinning black hole, this efficiency can climb even higher, approaching 40% in extreme cases. This makes accretion onto a black hole the most efficient energy conversion process known in nature, surpassing anything we can produce artificially. The radiation from these disks spans the electromagnetic spectrum, from radio waves to X-rays and beyond. In some systems, the inner edge of the disk glows so brightly in X-rays that it outshines the rest of the galaxy combined. In active galactic nuclei, where the central supermassive black hole is feeding rapidly, the sheer power of this output can alter the environment on galactic scales. But the energy release is not limited to radiation. In many black hole systems, we see powerful jets of plasma launched from the regions near the poles. These jets are narrow, collimated streams of particles accelerated to speeds approaching that of light. They can extend for thousands or even millions of light years, carrying energy far beyond the immediate surroundings of the black hole. The mechanism that drives them is still an area of active research, but it is thought to involve strong magnetic fields anchored in the accretion disk or threading the black hole's ergosphere, the region outside the event horizon where space-time is dragged around by the black hole's rotation. One leading explanation, the Blandford-Znajek process, describes how a rotating black hole can transfer some of its rotational energy to the surrounding magnetic field, which then accelerates particles outward in the form of jets. In this sense, the black hole's spin acts as a kind of flywheel, storing enormous amounts of energy that can be tapped under the right conditions. Over time, the extraction of this energy can slow the rotation of the black hole, although for many astrophysical systems the effect is negligible compared to the total spin energy available. The scale of these jets is difficult to grasp. Imagine a structure so vast that it spans more than the diameter of its host galaxy, moving with such precision that it maintains its narrow shape over millions of light years. As the jets plough into intergalactic space, they can inflate enormous lobes of hot plasma, visible in radio wavelengths that mark the regions where their energy is deposited. These lobes can influence the motion of gas in galaxy clusters, suppressing cooling flows and altering the conditions for star formation across vast volumes. In stellar mass black holes, the same processes occur on much smaller scales. These systems, often called microquasars, can still produce jets and outbursts that rival the power output of entire stars. Because their smaller size means that changes happen more quickly, microquasars allow astronomers to study the physics of accretion and jet formation in real time, observing shifts in brightness and jet behaviour over hours or days instead of years or centuries. Black holes can also act as engines in a more subtle way, by stirring and heating the gas in their host galaxies. As matter falls in and radiates energy, some of that energy escapes in winds and outflows that do not form narrow jets, but instead push on the surrounding medium more broadly. In galaxy clusters, where the central galaxy hosts a supermassive black hole, this feedback can keep large reservoirs of gas from cooling and condensing into stars. Without such feedback, clusters would likely form stars at rates far higher than we observe today. This feedback is not always destructive in the sense of halting star formation. In some cases, the compression of gas by expanding outflows can trigger new bursts of star birth in certain regions. The interplay between heating and compression makes black hole feedback a complex dynamic influence on galactic ecosystems, one that astronomers are still working to fully understand. It's worth noting that the idea of a black hole as an engine is not just a poetic metaphor. The processes at work here genuinely involve the conversion of one form of energy into another, subject to the same conservation laws and efficiencies that govern any machine. The input is gravitational potential energy and rotational energy. The output is radiation, kinetic energy in jets and winds, and in the long run, changes in the large-scale structure of matter in the universe. Some theoretical work has even explored whether an advanced civilization could, in principle, harness this energy in a controlled way. Concepts like the Penrose process, which extracts energy from a rotating black hole by sending matter into the ergosphere, show that it is possible in theory to tap the spin of a black hole. While such ideas are firmly in the realm of speculation for now, they highlight the extraordinary potential locked up in these cosmic engines. Even without the intervention of any intelligence, black holes naturally release and redistribute energy on colossal scales. This is why they are not merely passive endpoints for matter, but active participants in shaping the universe. Their influence extends far beyond the event horizon, altering the fate of gas clouds, the birth of stars, and the growth of galaxies. In the cosmic story, black holes occupy a dual role. They are destroyers in the sense that they consume matter and remove it from the observable universe, but they are also creators in the sense that their energy output drives processes that would not occur otherwise. They can light up the hearts of galaxies, sculpt their surroundings, and send energy racing across intergalactic space. This duality is part of what makes them so fascinating. A black hole's event horizon may mark the ultimate one-way boundary, but just outside it, in the maelstrom of the accretion disk and the launch points of jets, lies some of the most dynamic and energetic activity the universe has to offer. These are the places where gravity, magnetism, and relativity meet in their most extreme forms, producing phenomena that are as beautiful as they are powerful. The phrase "point of no return" carries meaning far beyond its astronomical definition. In the context of black holes, it is the event horizon, the boundary past which escape is impossible, that earns this name. But even as it describes a precise calculable surface in the geometry of space-time, it also carries with it a kind of philosophical gravity. There is something deeply human about the idea of a moment, a place, or a threshold after which the path forward is irreversible. The cosmos provides the literal version. Our minds can't help but think about the figurative one. In space, this boundary is absolute. There is no negotiation, no choice, no appeal. Once crossed, the outcome is inevitable, dictated by the structure of the universe itself. From the point of view of an outside observer, nothing can return. From the perspective of the traveller, there is no stopping, no pause, no way to undo the crossing. That stark inevitability is what makes it both terrifying and strangely comforting. It removes uncertainty entirely. There is no maybe once you're beyond that line. For much of human history, our sense of boundaries has been shaped by the possibility of retreat. You can walk toward a cliff and step back. You can set sail and turn the ship around. Even when risk is great, the option of reversal remains in some form. The event horizon is not like this. It is not a danger you can skirt at the last second. The decision, if you could call it that, happens long before the moment of crossing, because the physics will not allow you to fight against the pull once you are too close. In the equations of general relativity, the inevitability of the horizon comes from the way it reshapes what we mean by space and time. Outside the black hole, you can move in space in many directions while time moves inexorably forward. Inside, one of those spatial directions, toward the singularity, becomes as inevitable as time itself. You're not moving down toward the singularity, you're simply moving into your own future, and that future contains nothing but the singularity. It is the kind of shift in perspective that is hard to grasp without stepping outside our normal human intuitions. This, perhaps, is where the philosophical weight begins to grow. The event horizon is a reminder that some boundaries are not simply barriers. They are changes in the very nature of possibility. Before crossing, you can imagine a range of outcomes. After crossing, there is only one. In life, there are decisions and events that function in much the same way. Once taken, they close off entire branches of the future, leaving a single path ahead. The language of physics here is precise, but the resonance is broad. The point of no return is part of our stories, our myths, our private choices. It appears in the form of commitments we cannot undo, moments when something changes in a way that we cannot unchange. Sometimes we see them coming, sometimes we realize only afterward that we have passed through one. In this sense, the black hole's horizon is a perfect metaphor, even if it is born from a place where metaphors lose their footing. What makes the cosmic version so compelling is that it is utterly indifferent. The horizon does not judge, does not decide, does not care. It is not a guardian or a sentry. It is simply a property of space-time. There is no malice in its pull, no intention in its silence. We supply those qualities ourselves because we cannot help but tell stories about the forces we encounter, whether they are natural or human-made. It is also worth noting that the point of no return is not, for the falling traveller, the end of the experience. Cross it, and the journey continues, perhaps briefly, perhaps for what feels like some time, depending on the black hole's size. For a supermassive black hole, the tidal forces at the horizon may be negligible. You might notice nothing at all in the moment of crossing. The boundary's significance lies not in a sensory change, but in what the mathematics says about your fate. This too has its philosophical parallel. There are moments in life when you do not realize until later that you passed a boundary that altered everything to come. The inevitability of the horizon also raises questions about free will in the broader universe. If space-time can be arranged in such a way that the future path of an object is fixed regardless of its efforts, what does that say about the nature of choice? Of course, outside black holes, our everyday experiences are not so constrained. But the horizon is a vivid example of how the laws of physics can set limits that are not just difficult to overcome, but fundamentally impossible. Some thinkers have suggested that contemplating the event horizon is a way of confronting our own limits. Not just physical limits, but the limits of knowledge and action. We may imagine, for example, that with enough effort or technology, we could overcome any obstacle. The horizon reminds us that nature is not obliged to accommodate that optimism. There are regions of reality that we can describe but never reach, places we can predict but never visit and return from. There is also a certain humility in realizing that the universe contains boundaries that are absolute, not because they are enforced, but because they are built into the fabric of reality. The event horizon is not a wall that can crumble, nor a lock that can be picked. It is the shape of possibility itself around a black hole, and that shape cannot be altered without changing the laws that govern everything else. When we think about the point of no return in human terms, we often focus on regret or relief, depending on whether the path ahead seems worse or better than the paths left behind. In the context of a black hole, there is no such judgment. The horizon is neutral, the singularity inevitable. The emotional weight comes from our own projection onto that inevitability. It is in our nature to imagine ourselves in the place of the falling object, to feel the approach of that final boundary, and to wonder how we would meet it. This might be why the imagery of black holes appears so often in discussions that have little to do with astrophysics. It is shorthand for irreversible change, for the closing of doors, for the surrender to forces beyond our control. Yet the actual phenomenon is stranger and subtler than the metaphor suggests. It is not destruction in the ordinary sense, it is a continuation, but on a path that ends in a way that defies our current understanding. In contemplating the event horizon, we are invited to think about how we respond to finality, not the kind we can bargain with, but the kind that is written into the structure of things. Do we resist until the last possible moment? Do we accept and turn our attention inward? Do we spend our time before the crossing trying to understand, or do we simply experience? These questions have no scientific answer, but the science gives them a shape in the form of the horizon. Perhaps this is the deepest philosophical weight of the point of no return. It is a reminder that not all journeys are meant to be completed in the way we might wish. Some end where they must, not where we would prefer. And in that inevitability there is both loss and clarity. The horizon takes away the illusion of choice, but it also removes the burden of uncertainty. Beyond it, there is no wondering what might happen next. The future is set, and all that remains is to follow it to its conclusion. The image of drifting beyond the horizon is one of silence, not the silence of an empty room or a pause in a conversation, but the kind that exists when there is no medium left to carry sound at all. No air, no vibration, nothing but the void. It is the kind of quiet that comes not from muting the noise, but from removing the possibility of noise altogether. To imagine such a place is to imagine the ultimate absence of connection with what lies behind you. Crossing into this realm is not an explosion of chaos. It is not the tearing and rending that so often fills fictional depictions of black holes. In reality, for a sufficiently large black hole, you could drift through the event horizon without feeling anything at all. The pull of gravity, while inescapable, would be smooth and steady. There would be no sudden shock, no visible barrier. One moment you would still be in a part of space where escape was theoretically possible. The next, you would be in a region where the rest of the universe is permanently out of reach. The oddness of this is that the crossing itself is not an event you could mark except by calculation. There is no physical seam in the fabric of spacetime to alert you to the fact that you've moved from one regime of reality to another. The shift is in what the future holds, not in what the present feels like. You could be watching the light from distant stars, the faint glow of galaxies scattered across the darkness, and nothing in their appearance would signal that your link to them had just been severed in the most permanent way possible. From the point of view of someone far away, you would never quite reach the horizon at all. Your approach would appear slower and slower, your signals taking longer to arrive, your image dimming and reddening until it faded from view. To them, it would be as if you were frozen just outside the threshold, forever on the verge but never crossing. But from your own perspective, there would be no such hesitation. You would pass through in a finite time, the journey continuing just as it had before, except that the geometry of space-time now funnels you inexorably inward. Inside, space itself becomes a kind of current you cannot swim against. The paths that once could lead you away now bend toward the singularity no matter what you do. You could fire engines, turn around, make every attempt to change course, and it would make no difference. The structure of reality in this region ensures that every future you could have leads to the same place. It is an environment where the very concept of elsewhere is shrinking until only one destination remains. The light that reaches you inside the horizon is also altered. You could still see the glow of the matter that fell in with you, perhaps the warped image of objects that entered before you. You could still see the light from behind you as it continues to pour inward. But the view outward would be distorted, as though the window to the universe you knew is collapsing into a smaller and smaller portion of your sky. The rest would be filled with the dark interior, the curvature of space drawing everything toward the same point ahead. This narrowing of what is visible mirrors the narrowing of possibility. It is not an abrupt shutter closing, but a gradual focusing, a compression of all paths and perspectives into one. If you imagine drifting in such a place, the sensation would not be one of collision or impact, but of inevitability slowly taking form, as though the universe itself is drawing its attention to a single point and taking you with it. The duration of this journey depends on the scale of the black hole. For a stellar mass black hole, the distance from the horizon to the singularity might be crossed in milliseconds. For a supermassive black hole, it could be minutes or even hours in your own frame of reference. In that time, there is no turning back, but there is still motion, still the sense of falling deeper into something whose end is certain but not yet here. It is in these final stages approaching the singularity that the tidal forces become overwhelming. Even for a supermassive black hole, there comes a point when the difference in gravitational pull between your head and your feet is so great that it stretches you along your path of motion and compresses you from the sides. In smaller black holes, this spaghettification happens long before the horizon, but here it is delayed, allowing a calm drift for much of the journey before the forces grow extreme. From outside, of course, none of this is visible. To the rest of the universe, you vanished as you reach the horizon, your signals cut off by the one-way nature of that boundary. The continuation of your journey is something no distant observer can witness. It exists entirely within your own frame of reference, carried forward by the curvature of space-time that now governs your future completely. To drift beyond the horizon is to enter a region of the universe that is both part of it and forever separate. The matter and energy inside still contribute to the black hole's gravity, still influence the motion of stars and gas far away. But the details of what happens there are hidden, not just by distance, but by the nature of causality itself. The outside can affect the inside by sending in more matter, by altering the spin or mass of the black hole, but the inside can never send anything back. This is the ultimate one-way transition, and perhaps that is why it carries such weight in our imagination. It is not simply an ending, but a continuation into a place that no longer shares its future with the rest of the cosmos. For you, time moves forward as it always has. For the universe outside, your timeline has been cut away, sealed off, no longer running alongside theirs. It is an act of separation that cannot be undone. In thinking about this, it's hard not to return to the human parallels. We drift beyond horizons in our lives too. Moments when we step into a space where the old connections no longer function, where the road ahead is ours alone and cannot be traced by those who remain behind. In both the cosmic and the personal sense, this is not always a tragedy. Sometimes it is simply the way of things. But it is always a threshold, and thresholds change us. As you imagine the drift, you can picture the light bending around you, the universe behind you shrinking into a distant glow, and the pull ahead growing stronger. There is no struggle here that can succeed. The point is not to resist, but to understand. The black hole does not consume in anger or malice. It is simply the shape that space-time takes when enough mass collapses into a small enough region. The horizon is the natural consequence of that geometry. To pass it is to follow the rules of the universe to their most extreme conclusion, and so the drifting continues until the singularity is no longer ahead but here. In the language of relativity, this is the end of your world line, the final point in the sequence of events that make up your existence in this region of space-time. What happens there at the singularity itself is beyond our current understanding. The equations of general relativity give no usable answer, and quantum gravity, whatever its final form, is still being worked out. In that sense, the singularity is not just the end of a journey, but the edge of our knowledge. From outside, the black hole remains, its horizon unchanged by the crossing of a single traveller. The stars continue to orbit, the galaxy continues to turn, and the silence beyond the horizon is matched only by the indifference of the cosmos to what has passed within. But for the traveller, the moment is total. The journey has reached its conclusion, not in an explosion or a sudden halt, but in the simple fact that there is no more next. If there is any comfort in this image, it may come from knowing that the horizon is not a place of destruction but of transition, that the drift beyond it is not a violent tearing away, but a movement into a different kind of existence, one from which we cannot send word, but one that still follows the same laws that govern everything else. In the end, the horizon is just a boundary, and boundaries are where the known meets the unknown. And here, we find ourselves on the quiet edge of the story. We have followed the pull of gravity from the outskirts of galaxies to the very rim of the event horizon, watched the slow dimming of light, and drifted past the last place where the universe can still reach us. We've lingered in the space where time bends and paths narrow, where the possible becomes the inevitable, and where the end of one journey folds into the beginning of something unknowable. It's strange how thinking about something so far away, so unreachable, can still leave a weight in the mind. Black holes, for all their silence, have a way of speaking to our sense of limits, and to our curiosity about what lies beyond them. They remind us that there are places in the universe that will always be hidden, no matter how hard we look, and that sometimes what we can't see is as much a part of the story as what we can. Thank you for being here, for sharing this time in the calm, unhurried space between questions and answers. If you found this journey soothing, or if you'd like to explore more of the universe in the same way, you can always stay with us, night after night, as we follow the threads of science into the quiet. Until then, may your thoughts drift where they will, and may the pull of sleep be as gentle as the pull of distant stars.